Hello there, and welcome to Science for Sleep, a place where curiosity slows down, thoughts soften, and big ideas are allowed to unfold at their own unhurried pace. Tonight, we're going to take a gentle step outward, far beyond familiar skies, beyond constellations you might recognize, and beyond anything that feels comfortably sized. We're going to talk about something so vast that even astronomers, people who deal with enormous distances for a living, had to stop, recalibrate, and quietly admit that their intuition wasn't quite prepared for it. Because this evening is about a galaxy. Not just any galaxy, but the largest one ever discovered. A structure so immense that calling it big doesn't really help much, and calling it huge barely scratches the surface. It's the kind of object that stretches the limits of language, numbers, and imagination all at once. The sort of thing that makes you pause, not out of shock, but out of a slow, thoughtful disbelief. Before we ease into that scale, let me ask you something simple. Where are you listening from right now? Maybe you're in bed, lights low, or already off. Maybe you're somewhere quieter than the day, letting the noise fade. And what time is it where you are? It's a fitting question, really, because while we're about to talk about distances measured in millions of light years, you're still here in this exact moment, anchored to a very specific place and time. The universe is good at holding both extremes at once. If you find this space calming, interesting, or simply a comfortable way to unwind, you're very welcome to like the video or subscribe if you'd like to return again. It helps this calm corner reach others who might be looking for something steady and unhurried to end their day. And now, with nothing to rush toward, we can begin easing into the story itself. When most of us picture a galaxy, we tend to imagine something already quite large. A glowing spiral, perhaps, with arms sweeping outward, billions of stars held together by gravity, slowly turning through space. That image alone is enough to feel overwhelming if you stop and think about it for more than a moment. Billions of stars, each one potentially hosting planets, each one separated by distances so vast that light itself takes years to travel between neighbours. And yet, even that picture turns out to be a modest one. Astronomy has a way of humbling expectations. Every time we think we've reached a comfortable upper limit, the universe seems to quietly reveal something larger, older, or more extreme than we planned for. For a long time, astronomers believed galaxies had a certain practical size range. There were small galaxies, medium ones, large spirals like our Milky Way, and giant ellipticals that sat at the centres of clusters. These were already staggeringly big, but they still fit within a mental framework that said, this is about as far as gravity can organise stars into a single system. Then, slowly and without fanfare, that framework began to crack. The discovery of the largest known galaxy didn't arrive with flashing lights or dramatic announcements. It emerged the way many astronomical surprises do, through careful observation, patient measurement, and a growing sense that something wasn't lining up quite right. At first, it looked like a typical massive galaxy, one of the biggest known certainly, but not fundamentally different. Its core appeared dense and luminous, its surroundings filled with stars that seemed to stretch farther than usual. But the more astronomers looked, the farther it kept going. Galaxies don't have hard edges. There's no cosmic border where stars suddenly stop and empty space begins. Instead, they fade gradually, with stars becoming more sparse the farther out you look. This makes defining a galaxy's size surprisingly tricky. Where exactly does it end? How faint can a star be before it no longer counts as part of the system? For most galaxies, this uncertainty doesn't matter much. Their outer regions fade within a range that still feels manageable. But with this particular galaxy, the faint outskirts extended far beyond what anyone expected. Stars kept appearing where models said there shouldn't be many at all. The halo of the galaxy, a vast spherical region of stars and dark matter, stretched outward like a quiet echo that refused to stop. To appreciate just how unusual this is, it helps to ground ourselves briefly in something familiar. The Milky Way, our home galaxy, is already enormous. From one edge of its visible disk to the other, it spans roughly 100,000 light-years. That means light, travelling at the fastest speed anything can move, takes 100,000 years to cross it. Every star you see in the night sky is part of that disk or its surrounding halo. And yet, compared to the largest known galaxy, the Milky Way begins to look almost modest. The giant galaxy we're exploring tonight stretches not hundreds of thousands, but millions of light-years across. Its stellar halo alone extends several times farther than the entire diameter of our galaxy. If you were to place the Milky Way at its centre, along with several neighbouring galaxies, they would all fit comfortably inside this single system, like small islands floating within an enormous diffuse sea of stars. This isn't just a galaxy with more stars. It's a galaxy that occupies a completely different scale of structure. What makes this especially difficult to imagine is that galaxies are already some of the largest organised objects in the universe. Beyond them, you mostly find clusters of galaxies, enormous groupings bound together by gravity but not considered single structures in the same way. This giant galaxy blurs that distinction. It behaves like one system moving together, shaped by a shared gravitational field. Yet it rivals small galaxy clusters in sheer size. For astronomers, this raised an immediate question. How could something like this form? Galaxies grow over time through mergers and gradual accumulation. Smaller galaxies fall together, collide, and eventually settle into a single larger system. This process is slow and often chaotic, taking billions of years. Even the Milky Way is still growing, quietly absorbing smaller satellite galaxies along its edges. But to reach the size of this cosmic giant, that process would have to operate on an extraordinary scale, sustained over vast stretches of cosmic history. There's also the role of dark matter, the invisible substance that makes up most of a galaxy's mass. Dark matter doesn't emit light, but it provides the gravitational scaffolding that allows galaxies to form and grow. In this giant system, the dark matter halo is immense, extending far beyond the visible stars, holding everything together with a gentle but persistent pull. Without that invisible framework, the galaxy would simply drift apart. Stars at the edges would escape into intergalactic space. Instead, they remain bound, moving slowly, faithfully, as part of something much larger than themselves. When astronomers began to calculate the full extent of this galaxy, they had to rely on extremely faint light, subtle motions of stars, and careful statistical analysis. This isn't the kind of object you see clearly in a single photograph. It reveals itself gradually through accumulated evidence, like a shape emerging from fog. Each new measurement pushed the boundary outward. Each confirmation made the numbers harder to ignore. Eventually it became clear that this wasn't just an outlier or a measurement error. It was genuinely, undeniably vast. And yet, despite its size, this galaxy is quiet. There are no dramatic bursts of star formation lighting it up. No violent collisions happening right now. Much of it is old, composed of stars that formed billions of years ago and have been drifting ever since. This gives the galaxy a calm, almost patient character. It doesn't announce itself loudly. It simply exists, immense and steady, occupying a region of space so large that it reshapes our sense of what a single galaxy can be. When people hear the word galaxy, most of them already picture something enormous, even if they don't quite know the numbers. A sprawling collection of stars glowing softly, rotating over billions of years. That picture alone feels comfortably big, safely beyond anything we could ever experience directly. And yet, as soon as you pause on the question itself, how big can a galaxy be? That comfortable sense of scale starts to wobble. It sounds like a simple question, almost childlike. Big compared to what? Big in which direction? Big in terms of stars, mass, brightness, or space occupied? Astronomers have learned the hard way that the universe rarely answers simple questions with simple numbers. The moment you try to define a limit, nature tends to respond by quietly stepping past it. For a long time, scientists assumed galaxies had a practical upper boundary. Gravity, after all, is not infinite in its reach. Objects only remain bound together if the gravitational pull holding them exceeds the tendency of everything to drift apart as the universe expands. Too large, and a galaxy should lose its grip on its outer stars. They should wander off, becoming part of intergalactic space. That assumption felt reasonable, neat, satisfying. Then observations began to complicate it. To understand why the question of size is so slippery, it helps to step back and look at what a galaxy actually is, not in poetic terms, but in physical ones. A galaxy is a gravitationally bound system. That's the key phrase astronomers care about. Stars, gas, dust, stellar remnants, and large amounts of dark matter all moving together under a shared gravitational influence. As long as those components remain bound, astronomers are willing to call the whole thing a single galaxy. Notice what's missing from that definition. There's no mention of brightness, shape, or sharp edges. No requirement that it be easy to see. No rule that says it must look like a neat spiral or a smooth ellipse. All that matters is gravity and cohesion. That's where size becomes a philosophical problem as much as a measurement one. Take our home system, the Milky Way. From one end of its bright disk to the other, it spans about 100,000 light-years. Beyond that disk lies a halo of older stars and globular clusters extending much farther, perhaps 200,000 or 300,000 light-years across. Already, depending on which stars you count, the size of our galaxy changes dramatically, and the Milky Way isn't even close to the largest galaxy astronomers know about. Some galaxies are elliptical giants, found at the centres of galaxy clusters. They don't have neat spiral arms. Instead, they're shaped more like stretched clouds of stars, thicker in the middle, fading gradually toward the edges. These galaxies can be several times wider than the Milky Way and contain trillions of stars. Even so, for decades, astronomers felt confident that they were approaching the upper end of the scale. Confidence in astronomy, however, has a habit of being temporary. Part of the difficulty lies in how galaxies fade. Stars are not evenly distributed. They are densest near the centre and become more sparse the farther out you look. At some point, the light becomes so faint that it blends into the background glow of the universe itself. Detecting stars at those distances requires extremely sensitive instruments and careful analysis. Earlier telescopes simply weren't capable of seeing that faint. So for a long time, galaxies appeared smaller not because they were smaller, but because we couldn't see their outskirts. As telescopes improved, astronomers began detecting stars farther and farther from galactic centres. Halos grew larger, boundaries crept outward, and with each expansion of our observational reach, the same question resurfaced, quietly but insistently. How big can this really get? The answer, it turns out, depends partly on patience. Galaxies are not static objects. They grow, slowly, relentlessly, over billions of years. Small galaxies merge into larger ones. Streams of stars are pulled in by gravity, stretched into long arcs as they settle into new orbits. Gas falls inward, forming new generations of stars. Dark matter halos merge and overlap, creating ever larger gravitational wells. This process is inefficient and messy, but it never truly stops. If a galaxy sits at the centre of a crowded environment, such as a dense galaxy cluster, it has more opportunities to grow. Neighbouring galaxies drift close. Gravity does the rest. Over cosmic time, one dominant system can emerge, absorbing others like a tide pulling in scattered debris. Even then, astronomers once believed there would be a ceiling. Eventually, the universe's expansion should win. Galaxies should stop growing beyond a certain scale because the outer regions would no longer remain bound. The biggest galaxy ever discovered forces scientists to confront the uncomfortable possibility that this ceiling is much higher than expected. One reason this galaxy challenges intuition is that it doesn't just have more stars packed into the same volume, it occupies more space, vast amounts of it. Its stellar halo extends outward for millions of light years, so diffuse that individual stars are separated by enormous distances, yet still moving together under the galaxy's gravitational influence. This raises an immediate question. At what point does a galaxy stop being a galaxy and start becoming something else, like a galaxy cluster? Clusters are also gravitationally bound, after all. They contain hundreds or thousands of galaxies, held together by enormous dark matter halos. The difference has always been that clusters contain many distinct galaxies, each with its own identity. But the largest galaxy blurs this distinction. Its outer regions are so extended that in some ways they resemble the diffuse light found in galaxy clusters, known as intra-cluster light. This is light from stars that have been stripped from their original galaxies and now drift freely within the cluster's gravitational field. The unsettling realization is that, in this giant galaxy, much of what we see may be the end result of countless mergers, stretched and smoothed until the stars no longer form obvious substructures. What remains is a single coherent system, vast and quiet, but undeniably unified. Another complication comes from dark matter. Dark matter halos are much larger than the visible portions of galaxies. They extend far beyond where stars can easily form, providing a deep gravitational well that can hold material at great distances. In the largest known galaxy, the dark matter halo is immense. Its gravitational influence reaches far beyond the visible stars, binding them together over distances that would otherwise seem impossible. Without dark matter, this structure simply could not exist. This brings us back to the original question: how big can a galaxy be? And reframes it slightly. Perhaps the better question is how large a gravitational system centered on a galaxy can grow before it stops behaving like a single object. So far, nature's answer appears to be larger than we expected. There is also a subtle human factor at play. Astronomers tend to classify things based on what they know how to measure. For decades, measuring extremely faint light over enormous areas of sky was simply impractical. As a result, galaxies were defined by what could be easily observed: bright cores, clear shapes, recognizable boundaries. As technology improved, those definitions began to stretch. Today, astronomers use sensitive detectors, long exposure times, and sophisticated data processing techniques to detect faint starlight that would have been invisible before. When they apply these tools to massive galaxies, the results are often surprising. Light extends farther. Structures appear smoother and larger. What once looked like empty space turns out to be gently populated by stars moving in slow, wide orbits. In some cases, the outskirts of galaxies were hiding in plain sight, masked by the glow of the night sky and the limitations of earlier instruments. The biggest galaxy ever discovered is, in many ways, a product of this improved vision, not because it suddenly appeared, but because we finally learned how to see it properly. And that leads to an important realization. The universe did not change. Our understanding did. When astronomers began to accept the true scale of this galaxy, they had to reconsider several long-held assumptions. Models of galaxy formation had to account for sustained growth over enormous periods. Simulations had to allow for halos merging into structures larger than previously thought stable. Even the distinction between galaxies and clusters required a second look. Yet, rather than breaking physics, the galaxy fits within it. Gravity still behaves as expected. Dark matter still provides the scaffolding. The expansion of the universe still operates. What changed was our sense of proportion. It's easy to underestimate how deeply scale affects intuition. Humans evolved to navigate distances measured in meters and kilometers, not light years. Even when we intellectually understand large numbers, our instincts struggle to keep up. 1 million of anything feels abstract. A million light-years borders on meaningless without context. This is why the size of the largest galaxy feels so unsettling. It doesn't just add another zero to familiar figures, it moves the goalposts entirely. Imagine standing at the centre of such a galaxy. Not physically, of course, but conceptually. Light from stars at the far edge would take millions of years to reach you. Civilizations could rise and fall on planets orbiting those stars, completely unaware of the galaxy's opposite side. Entire histories could unfold without ever intersecting. And yet, all of that would still belong to one system. This challenges the way we think about unity and separation on cosmic scales. What feels impossibly distant can still be part of a single structure, bound together by forces that operate patiently over time spans far longer than any human story. By the time the word galaxy comes up in everyday conversation, it already carries a lot of quiet assumptions. Most people imagine something elegant and familiar, perhaps a spiral shape seen from above, glowing softly against a black background, with a bright centre and arms that curl outward like slow-moving pinwheels. That image is not wrong, but it is only one interpretation, shaped as much by history and human preference as by physics itself. When astronomers say the word galaxy, they are not describing a shape, a colour, or even a specific appearance. They are naming a relationship. A galaxy, in its most basic scientific sense, is a collection of matter that is held together by its own gravity and behaves as a single, coherent system over long periods of time. That sounds simple enough until you start asking where such a system begins and where it ends. The trouble is that the universe does not draw clean lines. Stars do not sit politely within neat borders. Gas drifts. Dark matter, which outweighs everything else, does not glow or announce its presence. Light fades gradually, rather than stopping abruptly. So when astronomers talk about galaxies, they're always working with definitions that are practical rather than absolute, useful rather than perfect. Historically, this was not always the case. For much of human history, galaxies were not galaxies at all. They were smudges, faint misty patches of light in the sky that did not resolve into stars no matter how carefully observers looked. The word galaxy itself comes from the Greek word for milk, inspired by the appearance of the Milky Way as a pale band stretching across the night sky. For centuries, people argued about what those hazy regions actually were. Some believed they were clouds of gas within our own stellar system. Others suspected they might be distant star systems, unimaginably far away. The debate lasted until the early 20th century, when astronomers finally gathered enough evidence to confirm that these smudges were entire star systems in their own right, far beyond our own. At that moment, the universe expanded dramatically in the human mind. Even then, the early definition of a galaxy was shaped by what telescopes could see. Galaxies were defined by their bright regions, their dense cores, their obvious structures. Anything too faint or too spread out was often ignored, not because it wasn't there, but because it was difficult to measure. This observational bias lingered quietly for decades. As instruments improved, astronomers began to notice that galaxies were not as compact as they once thought. Around bright disks and dense cores lay vast halos of stars, globular clusters, and dark matter extending far beyond the visible edges. These halos were not decorative extras. They were fundamental components of the galaxy, influencing its motion, its stability, and its long-term evolution. Yet even as halos became part of the accepted picture, they were often treated as secondary features. The real galaxy was still thought of as the bright part, the region where stars formed, where structure was obvious, where light was easy to detect. That distinction starts to fall apart when you encounter a galaxy whose halo dominates everything else. To understand why, it helps to break down what astronomers actually consider when they decide whether something belongs to a galaxy. One key factor is motion. Stars that are gravitationally bound to a galaxy move in predictable ways, orbiting the centre or following elongated paths influenced by the galaxy's mass distribution. Even at great distances, if a star's motion indicates it is bound to the system, astronomers are inclined to include it. Another factor is origin. Stars that formed within a galaxy, or were pulled in during mergers and interactions, carry chemical signatures that distinguish them from unrelated background stars. By analysing the elements present in starlight, astronomers can trace a star's history and determine whether it likely belongs to a particular system. Then there is dark matter, the quiet majority. Galaxies sit inside dark matter halos that extend far beyond the visible stars. These halos define the true gravitational footprint of a galaxy. If stars and gas move in a way that reflects the influence of a single dark matter halo, that strongly suggests they are part of one galaxy, even if they are separated by enormous distances. When all of these factors align, astronomers are comfortable calling the structure a galaxy, no matter how large it becomes. This is where the largest known galaxy challenges intuition. Its stars are not arranged in a tidy disk. Its light does not drop off quickly. Instead, it forms a vast, diffuse envelope that stretches outward so gradually that the notion of an edge becomes almost meaningless. And yet, the motions of those stars, the influence of dark matter, and the system's overall coherence point to a single gravitational entity. Calling it anything else would be misleading. There is also the matter of time. Galaxies are defined not just by what they look like now, but by how they behave over billions of years. A temporary alignment of stars does not count. A passing stream of debris is not enough. To be a galaxy, the system must persist, maintaining its identity through cosmic history. The largest galaxy passes this test with ease. Its stars are old. Many formed early in the universe's history. Its structure has been shaped by countless mergers, slow accretion, and long periods of quiet evolution. Nothing about it suggests a fleeting or accidental arrangement. It is stable on timescales that dwarf human comprehension. At this point, the word galaxy begins to feel less like a category and more like a spectrum. On one end are small dwarf galaxies, faint and fragile, sometimes containing only a few million stars. On the other end are giants so vast that they overlap conceptually with galaxy clusters. In between lies a continuous range of forms, sizes, and histories. The boundaries are fuzzy because the universe itself is fuzzy at those scales. This fuzziness becomes especially apparent when astronomers study the environments where the largest galaxies live. These giants often sit at the centres of galaxy clusters, regions of space where hundreds or thousands of galaxies are bound together. Over time, the central galaxy grows by absorbing others, their stars stretched into long streams and eventually mixed into the larger system. In such environments, it can be difficult to say where the central galaxy ends and the cluster begins. Stars stripped from smaller galaxies may drift through the cluster's gravitational field, no longer clearly belonging to any single system. Some astronomers refer to this as intra-cluster light, a diffuse glow permeating the space between galaxies. The largest galaxy blurs this distinction further. Much of what might once have been classified as intra-cluster light appears to be dynamically connected to the galaxy itself. Its dark matter halo encompasses these stars. Their motions align with the galaxy's gravitational centre. From a physical standpoint, they belong. This realization forces astronomers to rethink older definitions that relied too heavily on visual appearance. Brightness alone is no longer sufficient. Shape is secondary. What matters is the invisible architecture of gravity and motion. There is a certain humility in this shift. It acknowledges that our categories are tools, not truths. We define galaxies in ways that help us understand the universe, but those definitions must adapt as our understanding deepens. It also highlights how much of the universe operates beyond direct human perception. The largest structures are often the quietest. They do not announce themselves with dramatic flares or obvious patterns. They reveal themselves slowly through careful measurement and patient interpretation. In the case of the largest galaxy, its true nature only became clear when astronomers combined multiple lines of evidence. deep imaging to detect faint stars, spectroscopic studies to analyse motion and composition, computer simulations to model how such a system could form and remain stable. No single observation was enough on its own. This layered approach reflects the modern understanding of what a galaxy is. Not a static picture, but a dynamic system shaped by gravity, time and chance. There is also an emotional component to this, whether scientists admit it or not. Galaxies have long been treated as islands in space, distinct entities separated by vast voids. The largest galaxy challenges that metaphor. It suggests that some islands are more like continents, with boundaries that stretch far beyond what we once thought shorelines could reach. For those studying galaxy formation, this is both exciting and unsettling. Models must account for growth on scales that were previously considered unlikely. Simulations must handle interactions spanning millions of light years. Assumptions about equilibrium and stability must be revisited. Yet none of this undermines the core idea of a galaxy. It refines it. A galaxy is not defined by how comfortable it feels to imagine. It is defined by what gravity can hold together over time. If gravity can bind stars across millions of light years into a single, coherent system, then that system earns the name, no matter how much it stretches the mind. It becomes easier to see why the question of size leads naturally to deeper questions about measurement. If galaxies do not have sharp edges, how do astronomers decide where to stop measuring? If faint stars matter as much as bright ones, how do we ensure we are not missing the outermost regions? Trying to measure the size of something that does not have a clear edge is one of the more quietly difficult tasks in astronomy. It sounds straightforward at first. You find an object, you look at how far it extends, and you write down a number. But galaxies are not like tables or buildings or even planets. They do not end where something solid stops. They thin out, they fade, they dissolve gradually into the background of the universe itself. And that makes judging their size less like using a ruler and more like deciding where a fog truly ends. Astronomers are very aware of this problem. In fact, most of the time they are not measuring a galaxy so much as negotiating with uncertainty. Every method they use comes with assumptions, limitations and trade-offs. When the object in question is the largest galaxy ever discovered, those challenges multiply quickly. One of the first tools astronomers rely on is light, or more precisely, how much of it they can detect. Galaxies shine because their stars shine. In dense regions, starlight overlaps and creates a bright, easily visible glow. In outer regions, stars are spread thinly, separated by vast distances. Their combined light becomes faint, sometimes barely distinguishable from the background glow of the universe. Early surveys simply could not see this faint light. Telescopes were not sensitive enough. Detectors were noisy, and long exposures were difficult to manage. As a result, galaxies appeared smaller than they really were. Their visible boundaries were defined by the limits of technology, not by physical reality. As instruments improved, astronomers began pushing those limits outward. Longer exposure times allowed more light to accumulate. Better detectors reduced noise. Sophisticated data processing techniques made it possible to tease out faint signals from overwhelming darkness. With each improvement, galaxies quietly grew. This process did not happen all at once. It unfolded over decades, sometimes producing results that surprised even seasoned researchers. A galaxy that had been studied for years would suddenly appear larger when observed with newer equipment, not because it had changed, but because we had learned how to see it more clearly. One of the most important developments in this effort was space-based observation. Telescopes placed above Earth's atmosphere avoid the blurring effects of air and light pollution. Instruments like the Hubble Space Telescope provided extraordinarily sharp images and the ability to observe very faint objects over long periods. Hubble did not just capture prettier pictures. It extended humanity's reach into the dim outskirts of galaxies. Even then, light alone was not enough. Astronomers quickly realized that brightness is a misleading guide to size. A galaxy might appear compact simply because its outer stars are faint, not because they are absent. To address this, researchers began measuring how stars move, not just how they shine. Stars orbit the center of their galaxy under the influence of gravity. The speed of those orbits depends on how much mass lies within them. By measuring the velocities of stars at different distances from the center, astronomers can infer how far the galaxy's gravitational influence extends. If stars far from the center are still moving in an orderly way, bound by gravity, that suggests the galaxy reaches at least that far. This technique relies on spectroscopy, the study of how light is shifted as stars move toward or away from us. When a star moves away, its light stretches slightly, becoming redder. When it moves toward us, the light compresses, becoming bluer. By measuring these shifts, astronomers can calculate stellar velocities with remarkable precision. In the largest galaxy, these measurements revealed something unexpected. Stars located at enormous distances from the center were still moving as if they were part of a single system. Their velocities did not drop off as quickly as models predicted. Instead, they remained consistent with a massive gravitational field extending far beyond the bright core. That gravitational field, of course, is dominated by dark matter. Dark matter does not emit light, but its presence is revealed through its effects on motion. In almost every galaxy studied, stars move faster than they should if only visible matter were present. This discrepancy grows larger in the outer regions, where stars should, by classical expectations, drift away. The fact that they do not tells astronomers that an unseen mass is holding them in place. In the largest galaxy, the dark matter halo is colossal. Its gravitational reach spans millions of light years, binding stars that would otherwise escape. Measuring the extent of this halo is one of the primary ways astronomers judge the true size of the galaxy. To do this, they combine observations of stellar motion with computer simulations. These simulations model how galaxies form and evolve under the influence of gravity, dark matter, and cosmic expansion. By adjusting parameters until the simulations match observations, astronomers can estimate the size and mass of structures that cannot be observed directly. Another technique involves tracing stellar populations. Stars carry chemical fingerprints that reveal their origins. Elements heavier than hydrogen and helium are forged in stars and spread through space by supernovae. As a result, stars formed in different environments, and at different times have distinct chemical compositions. By studying these compositions, astronomers can determine whether stars in the outer regions of a galaxy likely formed there or were acquired through mergers. In the largest galaxy, many outer stars show signs of having originated in smaller galaxies that were gradually absorbed. Over time, their stars were stretched into long streams and eventually mixed into the larger system. The presence of these stars, still moving in coherent patterns, supports the idea that they belong to the galaxy, even if they are extremely distant from its centre. There is also the method of surface brightness profiling. Astronomers measure how a galaxy's brightness changes with distance from its centre. This produces a curve showing how light density decreases outward. For many galaxies, this curve drops steeply, indicating a relatively compact structure. For the largest galaxy, the curve declines much more gradually, extending outward over vast distances. At some point, the brightness becomes so low that it is difficult to distinguish from background light. This is where judgment and statistical analysis come into play. Astronomers must decide whether faint signals represent genuine galactic stars or random fluctuations. They do this by comparing observations across multiple wavelengths, using control regions of sky, and applying rigorous thresholds for detection. None of this yields a single, crisp boundary. Instead, astronomers define sizes based on conventions. They might say a galaxy extends to the radius where its brightness falls below a certain level, or where stellar motions cease to show coherent rotation, or where the dark matter halo's influence becomes negligible compared to the surrounding cosmic environment. These definitions are imperfect, but they are consistent. and consistency is essential for comparing one galaxy to another. When the largest galaxy was measured using these methods, every approach pointed in the same direction. It was enormous by any standard. Its light extended farther. Its stars remained bound at greater distances. Its dark matter halo dwarfed those of more typical galaxies. No single measurement created this conclusion. The convergence of many did. Another subtle factor is distance itself. Measuring size requires knowing how far away the object is. Astronomers determine galactic distances using a variety of methods, including standard candles like certain types of stars whose intrinsic brightness is known. By comparing how bright they appear, researchers can calculate distance. Errors in distance measurements translate directly into errors in size. A galaxy that is farther away than believed is also larger than believed. Modern techniques have reduced these uncertainties significantly, but they still exist. In the case of the largest galaxy, distance estimates are well constrained, giving astronomers confidence that its immense size is real, not an illusion of perspective. It is worth noting that astronomers are cautious by nature. Claims of extremes are scrutinized carefully. Being the biggest or the oldest or the most massive invites skepticism. In this case, multiple independent teams using different data sets and methods arrived at similar conclusions. That convergence is what solidified the galaxy's status. There's also an element of humility in how astronomers phrase these results. They often say the largest known galaxy rather than the largest galaxy. This leaves the room for future discoveries. History suggests that somewhere out there, something even larger may be waiting, currently hidden by faintness or distance. Still, the existence of a galaxy this large forces a reassessment of what is measurable at all. It shows that even when edges are blurry and boundaries fade, careful observation and creative methodology can reveal structure on scales that once seemed unreachable. Perhaps the most striking thing about these measurements is how indirect they are. No one sees the galaxy all at once. No single image captures its full extent. Instead, its size emerges from patterns, motions, and faint signals pieced together over time. It is less like photographing a mountain, and more like mapping an ocean by studying currents, temperatures, and distant waves. This approach reflects the broader nature of astronomy. The universe rarely presents itself plainly. It requires inference, patience, and a willingness to revise assumptions. The largest galaxy is not just a record holder. It is a lesson in how knowledge grows, not by sudden revelation, but by steady accumulation. If astronomers were able to measure something so vast only recently, how did they first suspect it existed at all? What initial clues hinted that one galaxy might be stretching far beyond familiar limits, quietly occupying a volume of space that no single system was supposed to command? Long before anyone confidently stated that the largest known galaxy extended for millions of light years, there was only a sense that something felt off. Astronomy rarely begins with a dramatic revelation. More often, it starts with quiet discomfort, a number that doesn't quite fit, a pattern that refuses to settle, a result that looks ordinary until you place it next to everything else you know. The earliest hints did not announce themselves as evidence of a record-breaking galaxy. They appeared as small anomalies scattered across different observations, each one easy to overlook on its own. It was only much later, when these hints were laid side by side, that a larger picture began to take shape. One of the first clues came from radio astronomy rather than visible light. Radio telescopes are designed to detect emissions that the human eye cannot see, often produced by energetic processes involving magnetic fields and charged particles. Some galaxies emit powerful radio waves, especially those with active supermassive black holes at their centres. These emissions can extend far beyond the visible stars, forming enormous lobes of radio-bright material. For decades, astronomers had catalogued radio galaxies with impressive sizes, some stretching hundreds of thousands of light-years. These were already considered large by any reasonable standard. The radiolobes were understood as jets of energetic particles launched from the galaxy's core, slamming into surrounding space and lighting it up at radio wavelengths. Then, gradually, astronomers began encountering radio structures that seemed almost excessive. Certain radio sources appeared unusually extended, far larger than typical radio galaxies. At first, these were often dismissed as overlapping objects or chance alignments. After all, when you're observing faint signals across vast distances, coincidences are inevitable. Two unrelated sources can line up just right to mimic a single, enormous structure. But some of these objects resisted that explanation. As radio surveys improved in resolution and sensitivity, astronomers could trace the shapes of these radio emissions more clearly. Instead of looking like separate pieces, some appeared to be connected, symmetrical around a single centre, and aligned in a way that strongly suggested a common origin. The scale, however, was unsettling. These radio structures were spanning millions of light years. At first, the focus was on the radio emissions themselves, not the galaxies producing them. The assumption was that the visible galaxy at the centre must be relatively ordinary, with unusually energetic jets. That idea worked for a while. Radio galaxies are known for dramatic behaviour, after all. But when astronomers began examining the host galaxies more closely, another oddity emerged. The central galaxies associated with these vast radio structures were often massive elliptical galaxies, the kind typically found at the centres of galaxy clusters. That alone was not surprising. What was surprising was how faint and extended their stellar envelopes appeared when observed with deep optical imaging. In standard observations, these galaxies looked large but not extraordinary. Their cores were bright, their shapes smooth, their profiles familiar. Only when astronomers pushed their instruments to detect extremely faint light did the picture begin to change. The outer regions kept going. Stars appeared at distances far beyond what models predicted for even the largest known galaxies. These stars were sparse, widely separated, and incredibly faint, but they were there. More importantly, they were not randomly distributed. Their arrangement suggested they were part of a coherent system, rather than unrelated background stars. At first, this was treated cautiously. Detecting faint light is notoriously difficult. Small errors in background subtraction can create the illusion of extended structures. Astronomers are trained to distrust anything that looks too dramatic at the limits of detection. So they checked again, and again. Different telescopes, different wavelengths, different teams. Each time, the extended light persisted. The measurements varied slightly, but the overall conclusion remained the same. This galaxy's stellar halo was far larger than expected. Another hint came from the environment around the galaxy. It sat in a region of space that was not particularly crowded. Unlike the densest galaxy clusters, where frequent interactions can quickly strip stars and blur boundaries, this galaxy occupied a relatively calm neighbourhood. That made its size harder to explain. If it had grown so large through mergers, where were the obvious remnants? Where were the distinct streams and substructures that usually mark recent galactic cannibalism? Some were there, faint and subtle, but many had already been smoothed out. This suggested an ancient history of growth, stretched over billions of years, a slow accumulation rather than a series of violent recent collisions. This was another quiet clue. Size on this scale likely required time, a lot of it. As attention focused more closely on this system, astronomers began studying the motions of its stars. This is where the hints became harder to ignore. Stars at extreme distances from the centre were not drifting randomly. Their velocities showed patterns consistent with being gravitationally bound to the galaxy. If those stars were truly part of the system, the galaxy's gravitational reach had to be immense. That in turn implied a dark matter halo of extraordinary size and mass. At this stage, the word unusual began appearing more frequently in papers and discussions. Still, no one rushed to label it the biggest anything. Astronomy is conservative when it comes to records. The history of the field is full of claims that were later revised or overturned. Researchers wanted more evidence, more confirmation, more independent lines of inquiry. The radio observations continued to play a role. The enormous radio lobes associated with this galaxy were not just large. They were exceptionally well aligned and symmetrical, stretching outward in opposite directions over distances measured in millions of light years. This symmetry strongly suggested a single central engine operating over an extraordinarily long time. Maintaining such jets for that duration requires stability. The central, supermassive black hole must have been active, on and off, for hundreds of millions of years. The surrounding environment must have been gentle enough not to disrupt the jet significantly. All of this pointed to a galaxy that had existed in a relatively steady state for a very long time. Another subtle hint came from comparison. When astronomers placed this galaxy alongside others known for their size, patterns emerged. Its stellar halo was larger, its radio structure was more extended, its inferred dark matter halo exceeded expectations. No single comparison was definitive, but taken together they formed a consistent trend. It was bigger in every meaningful way. Even then there was hesitation. Some researchers wondered whether the outermost stars should truly be counted as part of the galaxy. Perhaps they belonged to the surrounding large-scale structure of the universe rather than the galaxy itself. This is where definitions discussed earlier became crucial. When motions, chemical signatures and gravitational modelling were combined, the balance tipped. The evidence increasingly supported the idea that these stars were not free-floating. They were members of the same system. Eventually the accumulation of hints reached a tipping point. What had once seemed like a collection of oddities now looked like pieces of a single explanation. This was not an ordinary galaxy with unusual features. It was an extraordinary galaxy whose true nature had been hidden by faintness and scale. When researchers finally assembled the data into a coherent picture, they realized they were looking at a structure spanning roughly 16 million light-years from end to end. That number alone was difficult to absorb. It was several dozen times the diameter of the Milky Way, large enough to contain thousands of galaxies like ours within its bounds. Only then did the conversation shift. The question was no longer whether the galaxy was unusually large. The question became how it had escaped notice for so long. The answer, as is often the case in astronomy, lay in a combination of factors. Its outer regions were extremely faint. Its growth had been gradual rather than violent. Its environment was relatively calm. And until recently, few surveys were designed to look for structures on such enormous scales. When the galaxy was formally described and named Alcyonius, it was not presented as a sudden discovery, but as the culmination of years of incremental insight. The name itself, drawn from mythology, hinted at scale and endurance rather than spectacle. Looking back, the first hints seem almost obvious. Extended radio lobes, faint but persistent stellar halos, unexpectedly coherent motions at vast distances. Each one was a whisper rather than a shout. Together they formed a message that took time to hear. What makes this story especially fitting for a quiet exploration of the universe is that nothing about it was rushed. The galaxy did not reveal itself in a single image or announcement. It emerged slowly, as understanding often does, through patience, skepticism, and the willingness to look again when something feels just slightly too large to ignore. As this realization settled in, astronomers naturally began asking deeper questions. If such a galaxy exists, what does it look like in detail? How is it structured? And how does one even begin to visualize something whose scale overwhelms normal comparison? The moment when astronomers finally accepted what they were looking at was not dramatic in the way popular stories often suggest. There was no single night where a telescope swung into position and revealed an impossibly vast shape glowing clearly against the dark. Instead, the discovery of this galaxy unfolded through a slow convergence of evidence, conversations, recalculations, and a growing sense that the universe was quietly asking for a reassessment of what had once seemed settled. By the time the picture became clear, the galaxy itself had already been there for billions of years, stretching across space without concern for whether anyone noticed. What changed was human perspective. At first, the object that would later be recognised as the largest known galaxy was simply another entry in radio surveys. Radio astronomers routinely scan the sky for large-scale emissions produced by energetic processes around supermassive black holes. These surveys produce enormous catalogues filled with objects that range from compact sources to sprawling structures with lobes extending far beyond their host galaxies. Among these entries, one stood out, but only slightly at first. The radio emission associated with it was extensive, far more extended than typical radio galaxies. Its two lobes stretched outward in opposite directions with remarkable symmetry, suggesting a single, stable central source. That symmetry alone made it interesting. A symmetry often points to interactions or disturbances, while symmetry implies longevity and balance. Still, large radio galaxies were not unheard of. Some were already known to span several million light-years. This object appeared to be on the larger end of that range, but not obviously beyond it, at least not yet. What made astronomers pause was how well organised it seemed despite its scale. The radio lobes were not chaotic or fragmented. They showed a coherence that hinted at sustained activity over immense periods of time. That kind of endurance is not trivial. Radio jets fade, they disperse, they are disrupted by their environment. For jets to remain visible across millions of light-years, the conditions must be unusually stable. Curiosity grew, but caution remained. The next step was to identify the host galaxy, the visible structure responsible for launching those radio jets. Using optical surveys, astronomers located a massive elliptical galaxy near the centre of the radio emission. On its own, it looked fairly typical for a central galaxy in a large-scale structure. Bright core, smooth light profile, nothing that screamed impossible. If the story had ended there, the galaxy might have remained a curiosity, a radio source with impressive reach but nothing fundamentally new. What changed everything was depth. As astronomers began examining deeper optical images, taken with longer exposures and more sensitive detectors, faint light began to appear around the galaxy. At first, this was subtle, a soft glow extending farther than expected, something that could easily be dismissed as background noise or scattered light. But it did not disappear when the analysis was refined. Instead, it became clearer. Stars appeared well beyond the region where astronomers would normally draw a boundary, then farther still, and farther again. Each time the detection threshold was pushed lower, more structure emerged. The halo of the galaxy was not tapering off in the way models predicted. It was sprawling. This was the first truly unsettling realization. The radio galaxy was not just associated with a large energetic structure. The galaxy itself was physically enormous. At this stage, skepticism intensified. Detecting faint starlight at extreme distances is notoriously difficult. Slight errors in background subtraction can create artificial halos. Astronomers are acutely aware of how easy it is to fool oneself when working at the edge of detectability. So the data was scrutinized again, using different methods and independent data sets. Other surveys were consulted. Infrared observations were examined, as they can sometimes reveal stars obscured or diluted in visible light. The extended structure persisted. Meanwhile, attention returned to the radio emission. Its sheer scale demanded explanation. When astronomers measured the distance between the farthest extents of the radio lobes, the number was staggering, roughly 16 million light-years from end to end. That figure alone was enough to force a pause. To put it in context, many galaxy clusters themselves are only a few million light-years across. This single structure, driven by one galaxy, rivaled or exceeded the size of some clusters. And yet, it remained centered on a single host. At this point, discussion shifted from curiosity to disbelief. How could a galaxy maintain coherent radio jets over such a distance? How could it possess a gravitational influence capable of binding stars so far from its centre? How could it have grown so large without obvious signs of recent disruption? Each of these questions was uncomfortable on its own. Together, they suggested something genuinely outside the expected range. The turning point came when astronomers began combining radio data, optical observations, and theoretical modelling into a unified analysis. This was no longer about a single wavelength or technique. It was about consistency across the entire picture. The radio jets implied long-term stability. The stellar halo implied enormous gravitational reach. The motions of stars, where measurable, suggested they were not random wanderers but members of a single system. The inferred dark matter halo had to be immense, larger than anything previously associated with a single galaxy. The galaxy was not just large in one sense, it was large in every sense that mattered. Only then did researchers begin to openly discuss the possibility that they were looking at the largest galaxy ever identified. Even then, the language was careful. Words like candidate and possible appeared frequently. Extreme claims require extreme confidence. But as the evidence accumulated, alternatives grew thinner. One possibility was that the radio structure was misleading, that the lobes were not actually connected to a single galaxy. Detailed analysis ruled this out. The symmetry and alignment were too precise. The central engine was clear. Another possibility was that the outer stars belonged not to the galaxy, but to a surrounding cluster. This was more subtle. The boundary between a massive galaxy and its environment can be fuzzy, but when astronomers modelled the motions and distribution of stars, the conclusion was the same. The stars were bound. The system behaved as one. When the galaxy was formally described and named Alcyonius, the choice of name was fitting. In mythology, Alcyonius was a giant who drew strength from the land itself. The astronomical namesake drew its strength from gravity and time, growing slowly, steadily, until it reached a scale few would have thought possible. What makes this discovery particularly striking is how unassuming it was for so long. Alcyonius was not hidden behind dust clouds, or located at the edge of the observable universe. It was visible in principle for years. The reason it escaped recognition was not secrecy, but subtlety. Its outer regions were too faint to notice without deliberate effort. Its growth was too gradual to leave dramatic scars. Its environment was calm enough to allow it to expand without constant disruption. In a sense, it was the opposite of flashy. This realization prompted a quiet reckoning within astronomy. If a galaxy this large could exist without being immediately obvious, what else might be out there? How many other systems have been underestimated simply because their outskirts lie below traditional detection thresholds? The discovery of Alcyonius did not invalidate existing theories of galaxy formation, but it stretched them. Models that once seemed sufficient now had to accommodate sustained growth over enormous scales. Simulations needed to allow for dark matter halos that could remain coherent across millions of light years. Assumptions about the practical limits of galactic size had to be softened. There was also a psychological shift. Astronomers are accustomed to thinking in vast terms, but even they rely on intuition shaped by experience. Alcyonius exceeded that intuition. It forced researchers to confront the fact that the universe is not obligated to respect human expectations, no matter how well-reasoned they may seem. Importantly, the discovery was not treated as an endpoint. It was a beginning. Once Alcyonius was recognized for what it was, it became a reference point. Other large radio galaxies were re-examined. Data archives were revisited. New surveys were designed with greater sensitivity to faint, extended structures. The search expanded, informed by the lesson that size alone does not guarantee visibility. In that sense, meeting this galaxy was less like stumbling upon a monster, and more like realizing that the map itself had been incomplete. There is something quietly appropriate about that. the largest galaxy ever discovered did not announce itself with spectacle. It waited until observers were patient enough, careful enough, and humble enough to notice that the universe still had room to surprise them. At a certain point, numbers stop being useful in the way we expect them to be. They remain accurate, of course. They still describe reality with precision. But they lose their ability to connect with intuition. When astronomers say that a galaxy stretches for millions of light years, the words are correct, yet the meaning slides past the mind without ever quite landing. The scale is so far removed from everyday experience that the brain treats it less like information and more like a symbol for very large, then quietly moves on. This is the problem that emerges once the discovery of an object like this giant galaxy settles in. Understanding that it exists is one thing. Trying to picture it is something else entirely. Most people already struggle with the size of familiar cosmic structures. The Earth feels large until you compare it to the Sun. The Sun feels immense until you place it alongside other stars. Stars feel enormous until you remember that the average distance between them is measured in light years. By the time you reach galaxies, intuition is already badly strained. And yet, the largest galaxy ever discovered pushes even that strained intuition beyond its limits. Let's begin with a comparison that usually helps, at least at first. Our home system, the Milky Way, spans roughly 100,000 light-years across its visible disk. That figure is already difficult to internalize. Light moving at nearly 300,000 kilometers per second takes 100,000 years to cross from one side to the other. Every star you have ever seen in the night sky is contained within that space. Now imagine laying down a ruler marked not in kilometers or miles, but in entire Milky Ways. Place one, then another, and another. Keep going. The largest known galaxy would require dozens of those markers laid end to end just to reach from one side of its stellar halo to the other. At that point, the comparison begins to break down. It's not just that the galaxy is wider, it's that its scale changes the nature of distance itself. Within the Milky Way, stars are separated by a few light years on average. In the outskirts of the giant galaxy, stars can be separated by tens or hundreds of light years, yet still belong to the same system. The concept of neighbourhood becomes diluted. Proximity no longer means closeness in any intuitive sense. This is where numbers start to lose their grounding. Saying 16 million light-years does not feel 16 times larger than 1 million light-years in the mind. Both feel equally abstract. Once you pass a certain threshold, magnitude flattens into vagueness. Astronomers are well aware of this limitation. They encounter it constantly when communicating scale, not just to the public but to one another. This is why comparisons and layered perspectives become essential. You don't try to grasp the whole at once. You build toward it gradually, like adjusting your eyes to darkness. One way to approach the scale is through time rather than space. Imagine a beam of light leaving one edge of this galaxy and travelling straight across to the other side. That light begins its journey before the earliest known human civilizations exist. It continues while empires rise and fall, while continents shift, while species appear and vanish. By the time it arrives, the entire course of human history has unfolded, and then some. Even this framing falls short because human history itself is a blink compared to cosmic time. Still, it offers a faint anchor. It tells you that this is not merely large, it is large in a way that dwarfs all familiar narratives. Another approach is to think in terms of motion. Galaxies are not static pictures. They rotate, evolve, and change shape over time. In a galaxy this vast, the orbital periods of stars in the outer regions can be measured in billions of years. A star near the edge may not have completed a single full orbit since the universe was young. That star is not rushing anywhere. It drifts slowly, faithfully, bound by gravity across distances that feel more like intergalactic space than part of a single object. And yet, it belongs. This creates a strange tension between unity and dispersion. The galaxy is one system, but its parts are so spread out that the usual sense of cohesion feels strained. It is less like a city and more like a continent, less like a continent and more like a faintly connected archipelago spanning a cosmic ocean. Even visualizations struggle at this point. Images of galaxies often rely on brightness to define structure. Bright cores, defined arms, clear outlines. The largest galaxy resists this treatment. Its outer regions are so faint that if you tried to visualize them honestly, the galaxy would almost disappear into the background. Most of its size is defined not by what you can see clearly, but by what you can infer. This is uncomfortable for the mind. Humans trust what they can see. When something is real but barely visible, it feels less substantial, even if it occupies an enormous volume. The galaxy's immensity hides in plain sight, not because it is small, but because it is diffuse. Trying to picture it accurately means letting go of the idea of sharp edges. There is no clear boundary where the galaxy ends. Instead, there is a gradual thinning. Stars become rarer. Light fades. Eventually, the density drops below what our instruments can reliably detect. At no point does the universe place a sign that says galaxy ends here. This is one reason why comparisons with everyday objects fail so quickly. You cannot scale this galaxy down to something familiar without losing the essence of what makes it strange. A scaled-down model with a hard edge misrepresents reality. A soft-edged model feels unsatisfying, so the mind searches for other anchors. One of the most effective is contrast. Consider a galaxy cluster, a collection of hundreds or thousands of galaxies bound together by gravity. These clusters are among the largest structures in the universe that can still be considered cohesive. Their sizes are measured in a few million light years. Now consider that this single galaxy rivals or exceeds that scale. That contrast forces a re-evaluation. If a galaxy can grow to the size of a cluster, then the categories we rely on are not as rigid as they once seemed. Size alone does not determine classification. Behavior does, motion does, gravitational coherence does. Still, the question remains, how does one hold such scale in mind without it slipping away? Astronomers often rely on mental scaffolding. They build from the familiar outward, even if the final structure is too large to fully grasp. They imagine the Milky Way, then imagine a galaxy several times larger, then several times larger again, repeating the process until the numbers align. Even then, the result is incomplete. There is always a sense that the true scale remains just beyond reach. This is not a failure of understanding. It is a natural consequence of being human. Our brains evolved to handle environments measured in meters and kilometers, to judge distances that matter for survival. The universe operates on scales that do not care whether they are intuitive. Gravity works just as well whether the distance is a meter or a million light years. Dark matter binds structures patiently, unconcerned with how strange the result feels to us. In that sense, the difficulty of picturing this galaxy is itself informative. It tells us we have reached a boundary where comprehension must shift from visualization to acceptance. You may not be able to picture it clearly, but you can understand how it behaves, how it formed, and how it fits into the larger structure of the universe. There is also something quietly calming about this realization. You're not meant to fully imagine everything the universe contains. Some things are too large, too slow, too diffuse. They exist whether or not they can be neatly held in the mind. The giant galaxy becomes less like an object and more like a condition. A region of space where gravity has quietly gathered matter over billions of years, extending farther and farther without urgency, without spectacle. Its scale is not dramatic in the way explosions are dramatic. It is dramatic in its patience. As you sit with that idea, it helps to remember that even astronomers do not walk around constantly visualizing these scales. They work with equations, simulations, and data, tools that bypass intuition altogether. When they do try to imagine the structures they study, they do so knowing that the picture will always be approximate, and that is enough. Trying to picture the scale of the largest galaxy is not about achieving a perfect mental image. It is about letting the mind stretch a little, then rest. About acknowledging that some aspects of reality are better approached indirectly, through comparison, implication, and quiet reflection. Once that shift happens, another question naturally rises. If this galaxy is so enormous, how does it compare concretely to the system we call home? Comparison is one of the few tools the human mind has when it comes to understanding extremes. When something becomes too large, too distant, or too unfamiliar, we instinctively reach for something we already know and place the unknown beside it. This does not make the unknown smaller, but it gives it context. In the case of the largest galaxy ever discovered, the most natural point of reference is the system we live in, the Milky Way. Not because the two are similar, but because the differences between them reveal just how far the universe can stretch a single idea. The Milky Way feels enormous from the inside. It contains hundreds of billions of stars. Its disk is wide enough that light needs 100,000 years to cross it. Its halo extends even farther, filled with ancient stars and globular clusters that trace some of the earliest chapters of galactic history. From a human perspective, this is already almost impossible to fully grasp, and yet in the broader cosmic landscape the Milky Way is best described as a fairly typical large spiral galaxy. That fact alone can feel unsettling. The giant galaxy discovered in recent years does not simply exceed the Milky Way by a modest margin. It exists on an entirely different tier of scale. Lining the two up side by side is not like comparing a house to a skyscraper. It is more like comparing a city to a continent, and even that analogy begins to strain before it truly captures the difference. One of the most immediate contrasts lies in sheer physical size. The Milky Way's visible disk, where most of its stars, gas and dust reside, spans roughly 100,000 light-years. Its stellar halo may reach 2 or 3 times that distance. Beyond that, the gravitational influence of its dark matter halo continues, but the density of stars drops off sharply. The giant galaxy, by contrast, does not taper off so quickly. Its stellar halo alone extends for millions of light-years. This is not a small difference scaled up. It is a fundamentally different distribution of matter. Stars that would be considered far outside any reasonable boundary of the Milky Way remain comfortably within the giant galaxy's gravitational domain. This has important implications for how each galaxy evolved. The Milky Way grew through a series of mergers and accretion events, absorbing smaller dwarf galaxies over billions of years. Evidence of this history is still visible today in the form of stellar streams, faint arcs of stars stretched across the halo, remnants of past encounters that have not yet fully blended into the larger system. These features tell a story of growth that, while ongoing, has been relatively measured. The giant galaxy's history appears to be similar in process, but radically different in scale. It has also grown through mergers, but far more extensively and over a much longer span of time. Many of the structures that would remain distinct in a smaller galaxy have already been smoothed out, stretched thin by gravity until they blend into a vast diffuse envelope. Where the Milky Way still wears its scars, the giant galaxy has had time to let them fade. Structure is another point of contrast. The Milky Way is a spiral galaxy. It has a disk, spiral arms, a central bar, and ongoing star formation fueled by clouds of gas and dust. New stars are still being born, especially in the arms where material is compressed and triggered into collapse. This gives the Milky Way a certain dynamism. It is active, evolving, and internally varied. The giant galaxy, on the other hand, is an elliptical system. It lacks a disk and spiral arms. Its stars orbit in many different directions rather than following a single plane. Star formation is minimal. Most of its stars formed long ago, and the supply of cold gas needed to create new ones has largely been exhausted or heated beyond usefulness. This difference in structure reflects a difference in life stage. The Milky Way is still in a relatively youthful phase, actively building and reshaping itself. The giant galaxy is ancient and settled, its major growth largely complete, its present state defined more by quiet persistence than by dramatic change. Dark matter further amplifies the contrast. Both galaxies sit within dark matter halos, but the scale of those halos is vastly different. The Milky Way's halo is large enough to bind its stars and satellite galaxies, but it remains modest compared to the one surrounding the giant galaxy. In that system, the dark matter halo extends across millions of light years, providing the gravitational glue that holds together stars separated by distances that would otherwise be unthinkable for a single galaxy. This has consequences for how each galaxy interacts with its surroundings. The Milky Way is part of a small group of galaxies, including Andromeda and several dozen dwarf companions. The group is gravitationally bound, and over time these galaxies will interact and merge. The Milky Way's future includes a collision with Andromeda, an event that will reshape both systems into a larger elliptical galaxy. The giant galaxy, by contrast, already occupies a dominant position. It has effectively completed the process that the Milky Way is only beginning. Many potential merger partners have already been absorbed. What remains is a massive, stable structure that exerts influence over a vast region of space. Perspective from within each galaxy also differs dramatically. From Earth's position inside the Milky Way, the galaxy fills the night sky. The band of stars we call the Milky Way stretches overhead, a reminder that we are embedded in something much larger than ourselves. Yet even that band represents only a thin slice through the galaxy's disk. Most of the Milky Way's mass and extent remains hidden from view. If one could observe the giant galaxy from within, the experience would be profoundly different. There would be no dense disk forming a bright band. Instead, the sky would likely appear more uniform, filled with stars in many directions, but with lower density overall. The sense of being inside a structure would be subtler, more diffuse. The galaxy's vastness would not announce itself with brightness, but with quiet consistency. Timescales provide another revealing contrast. Stars near the Sun orbit the centre of the Milky Way once every 200 million years or so. Over the galaxy's lifetime, they have completed many such orbits. This regularity allows for mixing and gradual evolution of structure. In the outer regions of the giant galaxy, orbital periods can stretch into billions of years. Some stars may not have completed a single full orbit since they became part of the system. Their motions are slow, deliberate, shaped by a gravitational field that extends far beyond anything we experience locally. This difference in dynamical timescale affects how quickly each galaxy responds to change. The Milky Way reacts relatively quickly, on cosmic terms, to mergers and disturbances. The giant galaxy responds slowly. Changes propagate across it at a glacial pace, measured in epochs rather than eras. Even the role each galaxy plays in the larger universe differs. The Milky Way is one of countless large spiral galaxies scattered throughout the cosmos. It is representative, not exceptional. This is comforting in a way. It suggests that the conditions that led to our existence are not rare. The giant galaxy, however, is exceptional by definition. It occupies the extreme end of the distribution. Its existence tells us not what is typical, but what is possible. It reveals the upper limits of galactic growth under the right conditions, stretched over immense spans of time. There is a temptation to frame this comparison as one of small versus large, ordinary versus extraordinary. But that framing misses something important. The Milky Way and the giant galaxy are not competitors in a cosmic contest. They are different expressions of the same underlying processes. Gravity, dark matter, cosmic expansion, and time shape both, simply to different degrees. Seen this way, the Milky Way is not diminished by the existence of something larger. Instead, it becomes part of a broader story, one where galaxies can follow many paths, some leading to modest active spirals, others to colossal ancient giants. Understanding this comparison also helps explain why the giant galaxy was so difficult to recognize. Astronomers were accustomed to thinking of galaxies within a certain range of scale. The Milky Way anchored that intuition. When something exceeded that anchor by such a wide margin, it did not immediately register as a single object. It looked like something else, something beyond the category. Only by carefully and patiently comparing it back to familiar systems did its true nature emerge. If the Milky Way represents one evolutionary path, and the giant galaxy another, what conditions lead a system to grow so vast? Why do some galaxies remain relatively compact while others expand to extraordinary scales? Once the shock of scale begins to settle, a deeper question quietly takes its place. Not how big this galaxy is, and not how it compares to the one we live in, but why anything like this exists at all. Galaxies are not required to grow this large. The universe would function just fine without them. Gravity could have organised matter into countless smaller systems and stopped there. And yet, under the right conditions, growth did not stop. It continued patiently, almost indifferently, until a single galaxy came to occupy a volume of space that feels far more like a region of the cosmos than a single object. Understanding why galaxies grow this big means stepping away from the idea that size is a goal or an endpoint. Galaxies do not strive to become massive. They simply respond to forces acting over long stretches of time. The largest ones are not special because they wanted to be large. They are special because nothing ever got in the way of their growth. At the centre of this story is gravity, a force that operates without preference or foresight. Gravity does not plan. It does not choose efficiency. It simply pulls. Wherever matter exists, gravity begins to gather it, slowly at first, then more decisively as mass accumulates. In the early universe, matter was distributed almost uniformly, with tiny fluctuations in density left over from the Big Bang. These fluctuations were small, but gravity amplified them relentlessly. Regions that were slightly denser than average began pulling in more matter. As they did, they became even denser, increasing their gravitational pull further. This feedback loop is the foundation of all large-scale structure in the universe. Stars, galaxies, and clusters all trace their origins back to these early imbalances, but gravity alone does not explain extreme size. What matters just as much is time. The universe is old, about 13.8 billion years old. That number is often quoted, but its significance is easy to miss. It represents an almost incomprehensible span during which gravity has been working continuously, uninterrupted on cosmic scales. Given enough time, even small advantages compound. A galaxy that begins slightly larger or more centrally located can, over billions of years, become vastly larger than its neighbours. This is especially true for galaxies that form in favourable environments. Location matters. A galaxy that forms near the centre of a large-scale structure, such as a filament of the cosmic web or a developing cluster, has access to more material. Gas flows along these filaments, feeding galaxies over long periods. Smaller galaxies drift inward along gravitational gradients, eventually merging with larger ones. This is not a rapid process. It unfolds slowly, often without dramatic collisions, more like a steady drizzle than a storm. In such environments, growth can continue almost indefinitely. Another critical ingredient is dark matter. Dark matter makes up most of the mass in the universe, and it is the primary architect of large-scale structure. Galaxies form inside dark matter halos, invisible but massive regions that provide the gravitational framework within which stars and gas can gather. These halos are not fixed in size. They grow by merging with other halos just as galaxies do. When two dark matter halos merge, the resulting halo is larger and more massive, capable of holding onto more material across greater distances. The galaxy at its centre benefits directly from this expanded gravitational reach. In the case of the largest galaxy ever discovered, the dark matter halo is extraordinary. It extends across millions of light years, binding stars that would otherwise drift away. Without such a halo, the galaxy could not exist in its observed form. Stars at those distances would not remain part of a single system. Dark matter also grows hierarchically. Small halos form first. Over time, they merge into larger ones. This process favours the growth of a few dominant structures rather than many evenly sized ones. In any given region of the universe, there tend to be winners and losers. The winners keep growing, the losers are absorbed. This brings us to mergers, one of the most important drivers of galactic growth. Galaxies grow in two main ways. They form stars from gas, and they merge with other galaxies. Star formation adds mass gradually, but it is limited by the availability of cold gas. Mergers, by contrast, can add enormous amounts of mass relatively quickly, especially when they involve large galaxies. In dense environments, mergers are common. Galaxies orbit one another, lose energy through gravitational interactions, and eventually collide. These collisions are not like car crashes. Stars are so far apart that direct collisions are rare. Instead, the galaxies pass through one another, their stars settling into new orbits within a shared gravitational potential. Over time, repeated mergers build larger and larger systems. For the largest galaxy, this process appears to have been both extensive and unusually gentle. Rather than experiencing a few dramatic collisions late in its history, it likely absorbed many smaller galaxies gradually over billions of years. This allowed their stars to spread out into a vast, diffuse halo, rather than remaining in distinct substructures. The result is a galaxy that is enormous but smooth, lacking the obvious scars of recent violence. Another factor that allows galaxies to grow so large is the absence of strong disruptive forces. In some environments, galaxies experience frequent interactions that strip away stars and gas, limiting growth. In others, energetic processes like intense star formation or active black holes can heat surrounding gas, preventing it from cooling and settling into the galaxy. The giant galaxy appears to have avoided the worst of these limiting factors. Its environment has been relatively calm. It has had access to material without being constantly disturbed. Its growth has been steady rather than chaotic. There is also the role of cosmic expansion to consider. The universe is expanding, and on the larger scales this expansion works against gravitational collapse. Beyond a certain distance, objects recede from one another faster than gravity can pull them together. This sets an effective limit on the size of bound structures. However, within dense regions, gravity can overcome expansion. The largest galaxy exists in such a region. Its dark matter halo is massive enough to counteract cosmic expansion over millions of light years. This allows it to remain coherent even as the universe around it stretches. Importantly, this balance is delicate. Not every galaxy can achieve it. Only those that accumulate enough mass early enough and remain in favourable locations can grow to such extremes. Feedback processes also play a subtle role. When galaxies form stars rapidly or host active supermassive black holes, they can generate powerful winds that expel gas, limiting further growth. In some cases, this feedback effectively regulates galaxy size. The largest galaxy seems to have experienced the feedback that was strong enough to prevent runaway star formation, but not so strong as to eject material entirely from its gravitational influence. Gas may have been heated and redistributed rather than expelled, allowing stars to form early and then decline without halting overall growth. Time again becomes crucial here. A galaxy that forms most of its stars early can then spend billions of years growing through mergers without the complications of ongoing intense star formation. This leads to a large, old, and relatively quiet system. There is also an element of chance. The universe is not perfectly uniform. Small differences in initial conditions can lead to large differences over time. A galaxy that happens to form at the intersection of several cosmic filaments with access to multiple streams of matter has an advantage. Another, slightly displaced, may remain modest in size forever. Over billions of years, these small advantages compound. The result is a wide range of galaxy sizes, from tiny dwarfs to colossal giants. It is tempting to ask whether there is a hard upper limit, a maximum size beyond which galaxies simply cannot grow. The existence of the largest known galaxy suggests that if such a limit exists, it is higher than previously thought. Or perhaps the limit is not defined by size alone, but by the availability of matter, the structure of dark matter halos, and the local balance between gravity and expansion. In this sense, the giant galaxy is not an anomaly so much as an extreme outcome of ordinary processes given extraordinary time and opportunity. Understanding why galaxies grow this big also reshapes how we think about cosmic history. It reminds us that the universe is not static. Structures evolve, merge, and change character over time. What we see today is a snapshot, not a final state. The Milky Way, for example, is still growing. It will merge with Andromeda in the future, forming a larger elliptical galaxy. Given enough time and the right conditions, even that system could continue to grow, though it is unlikely to reach the scale of the giant galaxy we have been discussing. Still, the possibility exists. Nothing in physics forbids it outright. Perhaps the most striking lesson is that size in the universe is not about drama. The largest galaxy did not grow through spectacular explosions or sudden transformations. It grew quietly, steadily, almost anonymously, over billions of years. Its enormity is the result of patience rather than violence. This perspective changes how we think about scale. Immensity does not require intensity. Sometimes, the biggest things are built through accumulation so slow that it feels almost like stillness. Another question begins to emerge naturally. If a galaxy can grow this large through such a long, quiet history, what does that history actually look like when traced through time? What stories are written into the starlight of such a system, and how much of the universe's past is preserved within it? When astronomers talk about the history of a galaxy like this one, they are not referring to a sequence of dramatic events neatly lined up like chapters in a book. There are no sharp timestamps carved into space, no labels saying this merger happened here, this transformation happened there. Instead, the history exists in fragments, encoded quietly in the properties of stars that have been shining for billions of years. To read that history, astronomers do not look for explosions or motion so much as they look for consistency, age, and subtle variation. In a galaxy this large, history is not loud. It is slow, layered, and extraordinarily patient. Starlight is the archive. Every star carries information about when and how it formed. Its colour, brightness, motion, and chemical makeup all act as clues. None of these tell a complete story on their own, but together they form a record that can be read, if carefully enough. In a small or medium-sized galaxy, this record is already complex. In a galaxy stretching across millions of light years, it becomes something closer to a geological timescale, with layers built up over nearly the entire lifetime of the universe. One of the first things astronomers noticed when studying the stars in this giant galaxy is how old they are. Most of the stellar population appears to have formed very early, within the first few billion years after the universe itself came into existence. This immediately sets the tone for its history. A galaxy dominated by old stars is not one that has been forming stars actively for a long time. It is one that did most of its star-making early, then settled into a quieter phase. This matters because star formation is not a gentle process. When stars form rapidly, they produce strong radiation, stellar winds, and eventually supernova explosions. These inject energy into the surrounding gas, stirring it up, sometimes pushing it out of the galaxy entirely. In galaxies where star formation continues at a high rate, the environment remains turbulent. Structures are reshaped. Gas clouds collapse and disperse. The system stays lively. The giant galaxy does not show signs of this prolonged turbulence. Its stars suggest an early burst of formation followed by a long extended calm. That early burst likely occurred when the universe was denser than it is now. Gas was more abundant. Dark matter halos were actively merging. Conditions were favourable for rapid star formation. During this period, the galaxy's core would have grown quickly. building up a large population of stars in a relatively short cosmic time. Then gradually, something changed. As gas was used up or heated, star formation slowed. The galaxy transitioned into a quieter state. New stars became rare. Existing stars aged, evolving slowly through their life cycles. The galaxy did not stop growing, but its growth changed character. Instead of forming many new stars, it began to grow primarily by absorbing stars that had already formed elsewhere. This is where the slow history becomes especially important. Over billions of years, smaller galaxies drifted close enough to be captured by the giant's gravity. Some were torn apart completely. Their stars stretched into long streams before dispersing into the larger halo. Others merged more directly, their cores sinking inward, while their outer stars were flung far from the centre. Each of these events added material but not chaos. Because these mergers were spread out over immense spans of time, their effects were smoothed. Streams faded, motions mixed. What remained was a vast diffuse halo of stars that no longer carried obvious signs of their separate origins. The galaxy's outer regions became a kind of stellar sediment, layers upon layers of accumulated history. This is why the giant galaxy's halo is so extended and so uniform. It is not the product of a few recent collisions, but the end result of countless quiet incorporations, stretched thin by time. Chemical signatures reinforce this picture. Stars formed early in the universe contain fewer heavy elements than stars formed later. Heavier elements are produced inside stars and spread through space by supernovae. Over time, each new generation of stars is born from gas enriched by previous generations. By measuring the abundance of these elements in stars at different locations within the galaxy, astronomers can trace the sequence of growth. In the giant galaxy, stars near the centre tend to be slightly more enriched, while stars in the outer halo are more chemically primitive. This gradient is subtle but consistent. It suggests that the core formed early and quickly, while the outer regions were built up from many smaller systems that formed their stars early as well, then were absorbed. The fact that these chemical patterns remain coherent across such enormous distances is remarkable. It implies that the galaxy's history is not random. There is structure to it, even if that structure is only visible through careful statistical study. Motion tells another part of the story. Stars in a galaxy do not move arbitrarily. Their orbits are shaped by the gravitational potential of the system. In spiral galaxies like the Milky Way, many stars follow roughly circular paths in a disk. In elliptical galaxies, motions are more varied, with stars moving in many directions. In the giant galaxy, stellar motions show a clear pattern of belonging. Even stars located millions of light-years from the centre move in ways that indicate they are bound to the same gravitational system. Their velocities are slow, measured in tens or hundreds of kilometres per second, but they are consistent with the influence of a single, massive dark matter halo. This is one of the strongest pieces of evidence for the galaxy's long-term stability. A system that large could not remain coherent if it had experienced recent violent disturbances. The motions would be more chaotic. Instead, what astronomers see is order stretched across an extraordinary scale. Time smooths everything. This is perhaps the most important principle when thinking about the history written in the starlight of such a galaxy. Given enough time, sharp features blur. Distinct events overlap. The details of individual mergers fade, leaving only their cumulative effect. That does not mean the history is lost. It means it must be read differently. Instead of asking what happened at a specific moment, astronomers ask what patterns persist. They look for gradients, correlations, and distributions. They study how brightness changes with distance, how stellar ages vary, how motions shift gradually rather than abruptly. In doing so, they reconstruct not a timeline but a character. The character of this galaxy is one of longevity and patience. It did not rush to its current state. It did not need to. The universe gave it time, and gravity did the rest. there is also evidence that the galaxy's central supermassive black hole played a role in shaping this quiet history. Early on, when gas was abundant, the black hole likely accreted material and released energy into its surroundings. This energy would have heated gas, preventing it from cooling and forming new stars too rapidly. This kind of feedback can regulate star formation, leading to an early burst followed by a long decline. In this way, the black hole may have helped the galaxy settle into a stable configuration early in its life. Once that happened, growth could continue through mergers without the complications of intense internal activity. The radio jets associated with this galaxy offer a glimpse into that process. They indicate that the central black hole has been active intermittently over long periods, not constantly, not violently, but persistently enough to leave an imprint on scales measured in millions of light years. Those jets are part of the galaxy's history, but they are not the dominant theme. They are accents, not the melody. The melody is time itself, billions of years during which stars aged quietly, during which orbits carried them slowly around a centre they might never reach again within the current age of the universe, during which the galaxy expanded its influence not through conquest, but through accumulation. It is easy to think of history as something dramatic, something defined by turning points and sudden change. The giant galaxy challenges that instinct. Its history is defined by continuity, by processes that are almost boring in their regularity, except for the scale on which they operate. There is something deeply humbling about this. Human history is loud. It is filled with conflict, invention, collapse, and rebirth, all compressed into a few thousand years. The history of this galaxy makes that entire span feel like a momentary flicker, and yet the same physical laws apply. Gravity pulls, stars burn, matter moves. The difference is not in the rules, but in the patience with which they are allowed to play out. When astronomers say that the history of this galaxy is written in starlight, they mean that literally. Every photon carries information about the star that emitted it. By collecting enough of those photons from enough stars across enough distances, a story emerges. Not a story of sudden greatness, but of steady becoming. This perspective also reframes what it means to discover such a galaxy. We are not catching it at a special moment. We're seeing it in a long extended present, one that has lasted for billions of years and will likely continue for billions more. The galaxy is not finished. It is simply in a quiet phase of an ongoing existence. If this history has unfolded so slowly and left behind such an immense structure, what does that structure actually contain right now? What kinds of objects, from stars to clusters to unseen components, make up a galaxy of this scale? When you hear that a galaxy spans millions of light years, it is tempting to imagine that it must be packed with extraordinary things at every turn, as if immensity automatically implies excess. More stars, more planets, more activity, more everything. The reality is quieter, and in some ways more surprising. A galaxy this enormous is not dense or crowded. It is vast because it is spread out, not because it is overflowing. What lives inside it is defined less by spectacle and more by distribution, by how matter can remain connected across distances that feel almost empty by ordinary standards. To understand what inhabits a galaxy of this scale, it helps to let go of the idea that galaxies are filled uniformly. Even in the Milky Way, most of the volume is empty space. Stars are separated by light years. Planets occupy only tiny pockets around those stars. Gas and dust are thinly dispersed. The difference in a giant galaxy is not that this emptiness disappears, but that it stretches much farther. At the heart of the galaxy lies a dense core, similar in principle to the centres of other large elliptical galaxies. This region contains a very high concentration of stars, packed far more closely together than in the outskirts. Many of these stars are old, red, and long-lived. They formed early, when the universe was younger, and conditions favoured rapid star formation. Over time, they have settled into stable orbits, creating a luminous central region that anchors the rest of the galaxy gravitationally. Embedded within this core is a supermassive black hole. While it occupies an unimaginably small volume compared to the galaxy as a whole, its influence is outsized. The black hole's mass affects the motions of stars nearby and, during periods of activity, can shape the galaxy on scales far larger than its immediate surroundings. In this particular galaxy, the black hole has powered enormous radio jets in the past, sending energy outward across millions of light years. Those jets are among the most visible signs that something active resides at the centre, even if that activity is intermittent. Moving outward from the core, the stellar density begins to drop. There is no sharp transition, no point where one can say the central galaxy ends and something else begins. Instead, stars become gradually more sparse. This region is still very much part of the galaxy, but it already feels different. The stars here are more loosely bound, their orbits larger and slower, their paths shaped as much by the overall dark matter halo as by the luminous core. Many of these stars did not form in the galaxy's original core. They are immigrants, brought in through mergers with smaller galaxies over billions of years. Each merger added stars on wide orbits, expanding the galaxy's reach without dramatically increasing its brightness. Over time, these stars mix together, losing the clear signatures of their origins but retaining subtle chemical and dynamical clues that astronomers can still detect. Farther out still lies the region that challenges intuition the most. This is the extended stellar halo, stretching across distances so large that the word halo almost feels inadequate. Here, stars are incredibly sparse. You could travel for thousands of light years without encountering another star and still remain within the same galaxy. And yet these stars are not free-floating. They are gravitationally bound, moving slowly within the galaxy's immense dark matter framework. What lives here is not activity, but persistence. These outer stars are often among the oldest in the system. Many formed in small galaxies early in cosmic history, then were pulled into the growing giant. Their light is faint, their motion slow, but collectively they trace the true size of the galaxy. Without them, the galaxy would appear far smaller than it actually is. Interspersed among these stars are globular clusters. These are tight spherical collections of tens or hundreds of thousands of stars, bound together by their own gravity. Globular clusters are ancient, some nearly as old as the universe itself. In smaller galaxies, they tend to cluster closer to the centre. In the giant galaxy, they are found across an enormous range of distances, orbiting through the halo like slow-moving relics. Globular clusters are particularly valuable to astronomers because they act as test particles. By measuring their motions, researchers can map the galaxy's gravitational potential far from the centre. In a galaxy this large, globular clusters provide crucial evidence that the outer regions are indeed part of a single coherent system. Then there is gas, or rather the relative lack of it. Unlike spiral galaxies, which contain large amounts of cold gas and dust, fueling ongoing star formation, giant elliptical galaxies are mostly gas-poor when it comes to star-forming material. Much of their gas has either been used up, heated, or expelled over time. In the giant galaxy, gas exists primarily in hot, diffuse form, filling the space between stars at temperatures so high that it emits X-rays rather than visible light. This hot gas is not inert. It plays a role in regulating the galaxy's evolution. It interacts with radio jets from the central black hole, is stirred by mergers, and slowly cools over time. But it does not collapse readily into new stars. As a result, the galaxy remains largely quiescent, its stellar population aging rather than renewing itself. Beyond the stars and gas lies the most important component of all, dark matter. Dark matter dominates the mass of the galaxy and defines its true boundaries. The dark matter halo extends far beyond the visible stars, shaping their motions and holding the entire structure together. In the giant galaxy, this halo is immense. encompassing a volume of space that would otherwise be indistinguishable from the cosmic background. Nothing lives in the dark matter halo in the conventional sense. It does not form stars or planets. It does not emit light. But without it, nothing else could remain. It is the silent framework that allows stars separated by millions of light years to belong to the same system. There are also more subtle inhabitants, features that exist not as discrete objects but as patterns. Stellar streams, for example, are faint trails of stars left behind by disrupted galaxies. In many systems, these streams are visible as long, coherent arcs. In the giant galaxy, many such streams have already been smoothed out by time. Others may still exist, faint and difficult to detect, tracing ancient orbits that span enormous distances. These streams are the lingering fingerprints of past growth, remind us that the galaxy did not form all at once, but was assembled piece by piece. On even larger scales, the galaxy interacts with its surroundings. While it is a single system, it does not exist in isolation. It sits within the cosmic web, connected to filaments of dark matter and gas that span the universe. These connections are not something you could see by travelling through the galaxy, but they influence how material moves on the larger scales. In this sense, the galaxy is both self-contained and part of something larger. It is a node in a vast network, its size reflecting not just its own history, but the structure of the universe around it. What is striking about all of this is how little drama there is in the present moment. A galaxy this enormous is not bustling with activity. It is not exploding with new stars. It is not tearing itself apart. Most of what lives inside it is old, stable, and slow-moving. This quietness is not emptiness. It is maturity. The galaxy has already done most of its building. What remains is maintenance. Stars continue their long orbits. The central black hole occasionally stirs, sending energy outward. The hot gas shifts and settles. The dark matter halo remains steadfast. From a human perspective, it might feel anticlimactic. The largest galaxy ever discovered is not a fireworks display. It is more like a continent after the mountains have risen and the rivers have carved their paths, a place shaped by deep time rather than sudden events. There's also the matter of what does not live inside such a galaxy, at least not in abundance. There are likely fewer actively forming planetary systems than in spiral galaxies, fewer bright nebulae, less of the raw material associated with new beginnings. Life as we imagine it may be rarer here, simply because the conditions that favour it are less common. That does not make the galaxy barren. It makes it ancient. Every star inside it represents a chapter of cosmic history. Every globular cluster is a fossil from the early universe. Every faint outer star is a testament to gravity's patience. Together, they form a system that is not defined by what is happening now, but by everything that has already happened. As we consider what lives inside a galaxy this enormous, it becomes clear that size is not about excess. It is about reach, about how far influence can extend, about how long structures can endure. And that realization leads naturally to another question. If a single galaxy can contain so much history, so much mass, and so much space, how does its existence change what we thought we knew about the universe itself? How does finding something like this reshape our broader understanding not just of galaxies, but of the cosmic landscape they inhabit? The discovery of a galaxy this large does not overturn physics or invalidate everything astronomers thought they knew. Instead, it does something quieter and more unsettling. It stretches existing ideas to their limits and asks whether those limits were ever real to begin with. When an object appears that occupies a scale once thought improbable, the universe has not changed. Our mental boundaries have. For a long time, cosmology relied on a hierarchy that felt stable. Stars belong to galaxies. Galaxies belong to groups and clusters. Clusters belong to filaments and superclusters. Each level had a rough size range. a comfortable expectation that helped astronomers organize the universe into manageable layers. The largest galaxy ever discovered sits awkwardly within that hierarchy. It does not fit cleanly where we expected galaxies to end and larger structures to begin. That alone forces a reconsideration of classification. If a single galaxy can rival the size of small galaxy clusters, then size alone cannot be the defining feature that separates one cosmic structure from another. Instead, behavior becomes the key distinction. A galaxy is not defined by how much space it occupies, but by whether it behaves as a single gravitational system. This subtle shift in emphasis has broader consequences for how astronomers think about structure on the larger scales. One immediate implication concerns the way matter organizes itself in the universe. For decades, simulations of cosmic evolution have shown that matter flows along filaments of dark matter, gradually collecting into denser regions. These simulations successfully reproduce many observed features of the universe, including the distribution of galaxies and clusters. However, the existence of such an enormous galaxy suggests that under certain conditions, this flow can feed a single system for far longer and more efficiently than previously assumed. This means that the cosmic web may be even more flexible in its outcomes than models once suggested. The giant galaxy demonstrates that matter does not always distribute itself evenly among many systems. Sometimes it concentrates. Sometimes one structure becomes dominant, growing larger and larger while its neighbours are absorbed or left comparatively small. This reinforces the idea that cosmic evolution is not about uniformity, but about amplification. Small early differences can lead to dramatically different outcomes over billions of years. Another shift comes in how astronomers think about limits. In many areas of science, limits are comforting. They provide boundaries that simplify understanding. In astrophysics, limits are often expressed as maximum masses, maximum sizes, or maximum rates of growth. The largest galaxy ever discovered challenges some of those assumed ceilings, not by violating them outright, but by sitting so close to their edges that the edges themselves begin to blur. This does not mean there are no limits. Gravity still competes with cosmic expansion. Energy feedback still regulates growth. Dark matter halos still have finite extents. But it does mean that the practical limits may be higher and more context-dependent than previously thought. In other words, the universe allows more room for extremes than we were comfortable admitting. This realization ripples outward into how astronomers interpret observations. When a new object is detected, its size, mass, or brightness is often compared to known distributions. If it falls far outside the expected range, there is a temptation to suspect an error. Sometimes that suspicion is justified. Other times, as with this galaxy, it delays recognition. The existence of such a giant encourages greater openness to the unexpected. It reminds researchers that observational biases, especially toward bright and compact structures, can shape conclusions without anyone realizing it. Faint diffuse systems may be underrepresented simply because they are harder to see. This has consequences for surveys of the universe. Many large surveys are optimized to detect bright galaxies with clear edges. Objects that spread their light thinly across enormous areas are more difficult to identify and characterize. The giant galaxy suggests that there may be more massive systems hiding in plain sight, their outer regions blending into the background because they do not announce themselves clearly. As a result, astronomers are beginning to rethink how surveys are designed and analysed. There is increased interest in ultra-deep imaging, in techniques that enhance sensitivity to low surface brightness features, and in methods that combine data across wavelengths to reveal structures that would otherwise remain invisible. This does not just affect the study of galaxies, it affects how we map the universe as a whole. Another important shift concerns the role of dark matter. Dark matter has long been understood as the scaffolding of cosmic structure, but the giant galaxy highlights just how dominant that scaffolding can be. The dark matter halo of this galaxy is not a minor component. It defines the system. Without it, the galaxy would not exist in its observed form. This reinforces the idea that luminous matter, the stars and gas we can see, is only a tracer of a much larger invisible structure. Galaxies are not isolated islands of stars. They are visible manifestations of dark matter concentrations, shaped by the invisible far more than by the visible. In the case of the largest galaxy, this relationship becomes impossible to ignore. The stars occupy only a small fraction of the volume influenced by dark matter. Most of the galaxy's true size is defined by something we cannot see directly. That realization deepens an already humbling picture of the universe. There is also an impact on how astronomers think about time. The existence of such a galaxy underscores how slow and cumulative cosmic evolution can be. Human intuition often favours dramatic explanations. Big things must have dramatic origins. Yet this galaxy appears to be the product of steady growth, sustained over billions of years without the need for extraordinary events. This challenges the tendency to look for singular causes. Instead, it highlights the power of persistence. Given enough time, ordinary processes can produce extraordinary results. That lesson extends beyond galaxies. It applies to the formation of clusters, the shaping of large-scale structure, and even the thermal evolution of the universe. Many of the universe's most impressive features are not the result of sudden change, but of long-term accumulation. In that sense, the giant galaxy is not an anomaly. It is an extreme example of a general rule. The discovery also influences how astronomers think about the future. If galaxies can grow this large under the right conditions, what does that imply for the long-term evolution of cosmic structures? As the universe continues to expand, growth will eventually slow and stop. Dark energy will dominate. Structures will become increasingly isolated. But before that happens, there may be more time than previously assumed for large systems to continue growing. The giant galaxy suggests that some systems may already be approaching the upper limits of what gravity can assemble before cosmic expansion wins. Others may still be on their way. This reframes the present moment in cosmic history. We may be living during a period when the largest bound structures are nearing their maximum extent. The universe may never again be as structurally rich as it is now. That idea carries a quiet poignancy. There is also a philosophical shift that comes with discoveries like this. Humans tend to place themselves at the centre of narratives, even cosmic ones. We speak of the observable universe, of cosmic epochs, of beginnings and endings, as if these concepts revolve around our perspective. A galaxy that spans millions of light years and evolves over billions of years does not care about perspective. It existed long before humans looked up at the sky, and it will persist long after our species is gone. Its timescale dwarfs not just individual lives, but civilizations. This does not make human experience meaningless. It places it in context. The universe revealed by such a galaxy is one where significance is not tied to immediacy or drama. It is tied to endurance, to the ability of structures to persist, to accumulate, and to remain coherent across spans of space and time that feel almost unreal. There is also an impact on how astronomers communicate science. Discoveries like this highlight the gap between technical understanding and intuitive understanding. Scientists can describe the galaxy accurately using equations, simulations, and measurements, yet still struggle to convey what it means in a way that feels real. This encourages new approaches to explanation, ones that emphasize process over scale, history over snapshot, and behavior over appearance. The goal is not to make the universe feel small, but to make its vastness feel approachable. In that sense, the giant galaxy becomes a teaching tool. It shows how knowledge advances not by closing questions, but by opening them wider. Finally, the existence of such a galaxy reminds us that the universe is under no obligation to conform to our expectations. Patterns we observe are not guarantees, they are tendencies. And tendencies can produce outliers that redefine what we thought was normal. Astronomy has a long history of this. Each time we think we have found the biggest, the oldest, or the most extreme, the universe eventually presents something that forces a reassessment, not because the universe changed, but because our view of it became more complete. The giant galaxy fits squarely into that tradition. It does not shout. It does not disrupt. It simply exists, vast and patient, quietly expanding the range of what we know to be possible. If the universe allows structures of this size, where does it stop? Are there limits that truly cannot be crossed, or are they simply waiting to be nudged a little farther out by the next discovery? Once the existence of a galaxy this large is accepted, the mind naturally drifts toward a question that feels almost unavoidable. If something like this can exist, then where does it stop? Is there a true upper limit to how large a galaxy can become? Or are the boundaries we imagine simply artifacts of incomplete observation and cautious thinking? Astronomers have asked versions of this question for as long as they have tried to describe the universe in orderly terms. Limits are useful. They make problems tractable. They allow models to converge. But the universe has a long history of treating limits as suggestions rather than rules. At first glance, it seems reasonable to assume that galaxies must have a maximum size. Gravity, after all, is not infinitely strong. It weakens with distance. At some point, the expansion of the universe should overpower it, pulling matter apart faster than it can be held together. Beyond that point, structures should no longer remain bound. This idea is not wrong. It is incomplete. On the larger scales, cosmic expansion does dominate. Galaxies separated by vast distances recede from one another, carried apart by the stretching of space itself. No amount of gravity from an individual galaxy can pull in matter beyond a certain range. This sets an effective horizon, a scale beyond which growth is no longer possible. But the key phrase there is effective horizon, not a sharply defined boundary. The universe does not draw lines in space and say, growth stops here. Instead, there is a gradual transition where gravity's influence weakens and expansion takes over. In dense regions, gravity wins. In sparse regions, expansion dominates. The location of that transition depends on mass, environment, and time. A galaxy embedded in a particularly massive dark matter halo, located in a favourable region of the cosmic web, can maintain gravitational control over matter across surprisingly large distances. This is precisely what appears to have happened with the giant galaxy under discussion. Its sheer mass gives it leverage, its location gives it access, and its age gives it time. Together, these factors push the effective limit of galactic size much farther out than astronomers once expected. Another reason limits are difficult to pin down is that galaxies do not grow in isolation. They grow within a larger cosmic context that is itself evolving. Early in the universe's history, matter was closer together. The cosmic web was denser. Filaments fed growing structures efficiently. Under those conditions, it was easier for large systems to form and expand. As the universe aged and expanded, growth slowed. Distances increased. Matter became more diffuse. New galaxies still formed, but opportunities for extreme growth diminished. This suggests that the largest galaxies may be fossils of an earlier era, systems that began growing when conditions were unusually favourable and continued to do so long enough to reach extraordinary scales. If that is true, then size limits are not fixed numbers, but moving targets that depend on cosmic timing. There is also the question of definition. When astronomers ask how big a galaxy can be, they're implicitly asking where a galaxy ends. As discussed earlier, galaxies do not have hard edges. They fade gradually into their surroundings. Their dark matter halos extend far beyond their visible stars. Their influence blends into that of nearby structures. At some point, the distinction between a single galaxy and a larger system becomes semantic rather than physical. This is especially true at extreme scales. If a galaxy's dark matter halo overlaps with that of neighbouring systems, does it still make sense to treat them as separate entities? Or should they be considered part of a larger composite structure? Different criteria yield different answers. The giant galaxy highlights this ambiguity. Its size rivals that of small galaxy clusters, yet its stars and motions behave as a single system. Calling it a galaxy is justified by its coherence, even if its scale challenges traditional categories. This suggests that any hard limit on galactic size may be less meaningful than we would like. The universe does not operate in discrete boxes. It operates in gradients. There are, however, physical constraints that cannot be ignored. One of the most important is energy feedback. As galaxies grow, the processes within them can act to limit further growth. Star formation produces energy that heats surrounding gas. Supermassive black holes release enormous amounts of energy when they accrete matter. This energy can prevent gas from cooling and falling inward, effectively starving the galaxy of new material. In many galaxies, this feedback is strong enough to regulate size and mass. Growth slows. The system reaches a kind of equilibrium. The giant galaxy appears to have navigated this balance carefully. Feedback was present, but not so extreme that it shut down growth entirely. Instead, it may have redistributed gas rather than ejecting it, allowing the galaxy to continue growing through mergers even as star formation declined. This delicate balance is not guaranteed. It depends on timing, environment, and internal dynamics. Many galaxies likely attempted similar growth and failed, their expansion curtailed by energetic processes that cut off their supply. In this sense, the largest galaxy is not just large, it is fortunate. There is also the role of chance. Cosmic evolution is not deterministic in the way a simple equation is deterministic. Small variations in initial conditions can lead to vastly different outcomes. A slight difference in location within the cosmic web, a slightly earlier merger, a slightly more massive dark matter halo, all can cascade into dramatic differences over billions of years. The universe does not ensure that every region produces a giant galaxy. It allows for the possibility. Whether that possibility is realized depends on circumstance. This makes the idea of a universal maximum size less compelling. There may be practical upper bounds, but they are statistical rather than absolute. Most galaxies will fall well below them. A few will approach them. An even smaller number may brush against them, and each time one does, it will feel like a surprise. Another factor that complicates the idea of limits is observation itself. We can only measure what we can detect. Even with modern instruments, extremely faint structures are difficult to observe. The outermost regions of galaxies blend into background noise. Their stars are sparse, their light is weak. It is entirely possible that there are galaxies even larger than the one currently known, whose outer regions are so diffuse that they remain below detection thresholds. If so, our current record holder may not be the true upper limit, but simply the largest one we have managed to recognize so far. This possibility makes astronomers cautious. When they speak of the largest known galaxy, the emphasis is on known. History suggests that known is a temporary qualifier. The universe has repeatedly revealed that it is larger, older, and more extreme than expected when observational capabilities improve. There is no reason to believe that this pattern has ended. At the same time, there are reasons to believe that size cannot increase indefinitely. Cosmic expansion is accelerating due to dark energy. Over time, this acceleration will increasingly isolate gravitationally bound systems from one another. New mergers will become rarer. Growth will slow and eventually cease. In the very distant future, galaxies will be cut off from external material. What they have will be all they ever have. Under those conditions, no new giants will form. Existing ones will persist, but they will not grow much larger. This suggests that the present era may be special, a window during which extreme structures can still form and be observed. The giant galaxy may represent something close to the maximum size achievable under the laws of physics as they operate today. Or it may be one of several such systems, with others waiting to be discovered. The truth is, we do not yet know. What we do know is that the question of limits is less about finding a final number and more about understanding processes. It is about how gravity competes with expansion, how dark matter shapes structure, how feedback regulates growth, and how time amplifies small differences into large outcomes. In that context, the largest galaxy is not an endpoint. It is a data point, albeit an extreme one. It tells us that our previous assumptions about scale were incomplete. It tells us that the universe allows for more variety than tidy categories suggest. It tells us that patience, both cosmic and human, can yield results that feel almost unbelievable. There is also something quietly reassuring in the absence of hard limits. A universe with strict, easily defined boundaries can feel mechanical, predictable. A universe where boundaries blur, where extremes exist but are rare, feels more organic, more open-ended. The giant galaxy fits into that latter picture. It does not break the rules. It stretches them, and in doing so, it invites a more flexible way of thinking about cosmic structure. As astronomers continue to explore deeper, fainter, and wider regions of space, they will likely encounter more objects that test assumptions. Some will be smaller than expected. Others will be larger. Each will add nuance to our understanding. For now, the question of whether true limits exist remains open. Perhaps there is a maximum size set by the balance of forces in the universe. Perhaps we are close to it. Or perhaps size is constrained only by opportunity and time, and the universe is not yet exhausted either. What seems certain is that our intuition is not a reliable guide. The largest galaxy ever discovered reminds us that the universe is under no obligation to be intuitive, symmetrical, or convenient. It evolves according to simple laws applied over immense scales, producing outcomes that feel anything but simple. If structures of this size exist, and if limits are flexible rather than fixed, what does that mean for us here, in a comparatively small galaxy, on a small planet, living through a brief moment of cosmic time? When confronted with something as vast as the largest galaxy ever discovered, the natural instinct is to feel small. Not metaphorically small, but genuinely diminished in scale, as if the sheer size of the universe has somehow reduced the significance of everything closer to home. That reaction is understandable, but it is also misleading. Scale in the universe does not work the way importance works in human life. Bigger does not mean more meaningful, and smaller does not mean insignificant. Instead, size provides context, and context reshapes perspective. From where we are in one spiral arm of the Milky Way, it is easy to imagine our cosmic environment as substantial. Our galaxy feels immense when we look up at the night sky and see that pale band of starlight stretching overhead. It feels ancient, stable, and encompassing. And in practical terms, it is. Every human story that has ever unfolded has done so within this single galaxy. Every planet we have visited, every signal we have sent, every dream we have attached to the word space has existed entirely inside it. Learning that there are galaxies far larger does not take that away. What it does is adjust the frame. The giant galaxy does not replace the Milky Way as our home. It does not overshadow it in a way that erases its relevance. Instead, it shows that the universe is capable of hosting structures on a wide range of scales, all operating under the same basic laws. Our galaxy is one expression of those laws. The giant galaxy is another. From a physical standpoint, nothing changes for us. The stars in the Milky Way continue their slow orbits. The Sun continues to move around the galactic centre. Earth continues its quiet path around the Sun. The existence of a much larger galaxy elsewhere in the universe has no effect on the stability of our solar system, the rhythm of our days, or the conditions that allow life to exist here. And yet, psychologically, something does shift. There is a tendency to think of discovery as something that adds layers to reality, as if each new finding makes the universe more crowded or complex. In truth, discoveries like this often do the opposite. They simplify by expanding scale. They remind us that our everyday concerns occupy a very narrow band of existence, and that outside that band, time and space operate very differently. That realization can feel unsettling at first. Human life is built around immediacy. We care about years, decades, generations. The giant galaxy cares about none of these. Its history is measured in billions of years. Its present state is the result of processes so slow that change is almost imperceptible. Seen from that vantage point, our lives are brief flickers. But that brevity is not a flaw. It is a feature. Meaning does not come from duration alone. A galaxy can persist for billions of years without awareness. A human life, though short, contains experience, memory, curiosity, and reflection. The fact that we can even contemplate the existence of such a galaxy is remarkable in itself. There is also something grounding about knowing that we are not central to everything. For much of human history, it was comforting to imagine that our world, our star or our galaxy, occupied a privileged position in the universe. Each step away from that idea has been challenging. Earth is not the centre of the solar system. The Sun is not the centre of the galaxy. The Milky Way is not the centre of the universe. The discovery of an impossibly large galaxy continues that trend, not by diminishing us, but by freeing us from the expectation that everything must revolve around our perspective. We exist in a universe that is vast, old, and varied. Our value is not derived from being central within it, but from being conscious within it. There is also a quieter implication that is easy to miss. A galaxy this large exists because conditions allowed it to. Gravity had time, matter had freedom to accumulate, disruption was limited, nothing forced growth to stop early. That tells us something important about the universe we inhabit. It is not a place that rushes. It does not demand efficiency. It allows processes to unfold at their own pace. That same patience is what allowed life to emerge here. The Milky Way did not need to be the largest galaxy for planets to form, for chemistry to become complex, or for intelligence to arise. It needed stability, time, relative calm, and it had those things. In that sense, our galaxy is perfectly suited to us, regardless of how it compares in size to others. The giant galaxy highlights this distinction beautifully. It is enormous, but it is also quiet. It is not overflowing with new stars or violent change. Much of its mass exists in regions so sparse that interactions are rare. Life, as we understand it, may be far less likely there than in a more modest, actively star-forming spiral like our own. Bigness does not guarantee richness of experience. From our small corner of space, then, the existence of such a galaxy does not threaten meaning. It refines it. It shows that the universe produces many kinds of environments, each with its own character. Some are vast and ancient. Others are smaller and more dynamic. We happen to live in one that balances longevity with change, stability with creativity. There is also an ethical dimension to this perspective, subtle but real. When we recognize how small our physical footprint is compared to the structures of the universe, it becomes harder to justify treating our own world casually. Earth is not just small. It is rare in its ability to support life. The vast majority of space, including most of that giant galaxy, is inhospitable, cold, empty, silent. The fact that life exists at all, anywhere, becomes more precious against that backdrop. The giant galaxy also reminds us that discovery is ongoing. Our picture of the universe is not complete. It never has been. Each time we think we have mapped the extremes, something appears that stretches them. That does not mean the universe is chaotic or unknowable. It means that our understanding grows incrementally, shaped by tools, patience, and the willingness to revise assumptions. From our position inside the Milky Way, this is both humbling and empowering. Humbling, because it shows how much remains beyond our direct experience. Empowering, because it shows that even from a small planet orbiting an average star, It is possible to learn about structures millions of light years across. We do this not by travelling to them, but by thinking carefully, measuring precisely, and asking questions that do not assume the answers in advance. There is a poetic temptation here to turn this realization into something grand and abstract. But the more grounded truth is simpler. The universe does not require us to be large to matter. Our corner of space is small by cosmic standards, but it is dense with significance to us. It contains our history, our culture, our relationships, our questions. Those things do not scale with light years. They scale with awareness. In practical terms, the discovery of a giant galaxy also changes how we interpret future findings. It encourages caution when declaring boundaries. It encourages curiosity when data does not quite fit expectations. It encourages the idea that unusual does not mean impossible. This mindset applies not just to astronomy, but to exploration more broadly. Whether we're studying the universe, the Earth, or ourselves, the assumption that we already know the limits can quietly prevent discovery. The giant galaxy teaches a gentle lesson here. It did not need to announce itself dramatically to be real. It existed long before it was recognized. It will continue to exist regardless of how often it is mentioned. Its discovery depended not on its behavior, but on our readiness to see it. That lesson translates well to our own lives. Many meaningful things are quiet. They develop slowly. They do not draw attention to themselves. They become visible only when we slow down and look carefully. In that sense, the story of this galaxy fits surprisingly well into a human context. It is not a story about domination or spectacle. It is a story about accumulation, patience, and endurance. From here, in our small corner of space, that perspective can be oddly comforting. We do not need to be the biggest, the fastest, or the most extreme to belong in the universe. We belong because we are part of it. Because we are shaped by the same physical laws. Because the atoms in our bodies were forged in stars, some of which may have existed long before the giant galaxy finished assembling itself. We are not separate from that vastness. We are a localized expression of it. And perhaps that is the most meaningful implication of all. The universe is not something happening elsewhere, among distant galaxies and unreachable scales. It is happening here, continuously, in ways that intersect with our lives in subtle but profound ways. After spending so much time moving outward, stretching thought after thought across millions of light years, there comes a natural moment to let attention drift back inward again. Not abruptly, and not as a conclusion, but as a gradual return, the way your eyes adjust when you step back inside after looking at a wide open horizon for a long time. The universe does not collapse when you stop thinking about its larger structures. It continues exactly as it was. What changes is the way you carry that awareness with you. Even now, nothing about your immediate surroundings has shifted. Whatever room you're in still exists at the same scale. The sounds around you, if there are any, remain local and familiar. Your body occupies the same space it did before. And yet, having spent time with the idea of a galaxy stretching across millions of light years, those ordinary details can feel slightly different, framed by something much larger than themselves. That contrast is not meant to be dramatic. It is meant to be grounding. The immensity we have been exploring does not demand awe or insignificance. It does not require you to feel small. Instead, it offers a broader backdrop against which smallness no longer feels like a problem. When the universe is this vast, there is no pressure to be large in any particular way. From where you are, inside the Milky Way, the giant galaxy we have been discussing is unimaginably distant. Its existence does not intrude. It does not cast a shadow. It does not compete for attention. It simply exists elsewhere, part of the same universe, operating under the same physical laws, but on a scale that unfolds far beyond anything you need to engage with directly. That separation is important. Human minds are good at expanding outward, but they are not designed to live there permanently. If you stayed focused on cosmic scale all the time, everyday life would lose its texture, meaning would flatten, details would blur. The value of drifting back is that it restores balance. It allows the large and the small to coexist without one erasing the other. The giant galaxy does not replace your world, it contextualizes it. One of the quiet realizations that often emerges after contemplating cosmic immensity is that the universe does not rush. Growth on the larger scales happens slowly, sometimes so slowly that change is nearly imperceptible. The galaxy did not become enormous overnight. It accumulated mass patiently over billions of years without urgency or intent. That same lack of urgency can be carried inward. In daily life, there is a constant sense of movement, deadlines, progress, and pressure. Everything feels immediate. Everything feels as though it must happen now. The universe offers a different rhythm. It shows that meaningful change does not always announce itself, and that scale does not require speed. The giant galaxy grew because nothing forced it to stop early. That is all. This does not mean human life should imitate cosmic timelines. We live on shorter scales for good reason. But it does suggest that not everything needs to be resolved quickly. Some things benefit from time, from repetition, from accumulation so gradual it feels like stillness. As you let attention return to your own position in space, it can help to remember that the atoms making up your body did not originate here. They were formed in stars long before the Milky Way took its current shape. Some of them may have existed in galaxies that no longer exist, galaxies that were absorbed into larger ones. Their stars stretched thin and scattered, much like the process that built the giant galaxy itself. In that sense, you already carry cosmic history with you. The immensity is not external, it is embedded. This is not meant as a metaphor, it is a physical fact. The same processes that allow a galaxy to grow to impossible size also allowed heavier elements to form, planets to emerge, and chemistry to become complex enough for life. The universe did not pause to make room for these things. They arose naturally, as consequences of the same laws playing out at different scales. Understanding this does not require constant contemplation. It simply means that the vastness does not need to be held tightly. It can rest in the background, informing perspective without demanding attention. There is a subtle difference between ending an exploration and letting it settle. Ending implies closure. Settling implies continuity. The giant galaxy does not represent an endpoint in understanding. It is part of an ongoing story about how the universe organizes itself, how matter responds to gravity over long periods, and how limits tend to soften rather than harden when examined closely. New observations will refine this picture. Other systems may be found that rival or exceed it, or perhaps not. Either outcome fits comfortably within what we now know. What matters more is how this knowledge integrates into your sense of place. From Earth, the universe can feel abstract, distant, and disconnected. Concepts like millions of light years and billions of years sound impressive, but they can also feel empty if they are not grounded. Drifting back down to Earth does not diminish those scales. It gives them somewhere to land. Your location in space is specific. Your moment in time is specific. Those specifics do not contradict cosmic immensity. They coexist with it. The giant galaxy is quiet. It does not send messages. It does not demand interpretation. It simply persists. In doing so, it offers a kind of permission. Permission to exist without urgency. Permission to take up space without justification. Permission to be part of something larger without needing to understand all of it at once. This is especially important when thinking about the future. The universe will continue to expand. Galaxies will drift farther apart. Some structures will become isolated. The giant galaxy will still be there, bound within its own dark matter halo, evolving slowly. The Milky Way will also continue, changing shape over time, merging with its neighbours, becoming something different from what it is now. None of that requires your attention in this moment. Right now, it is enough to know that such processes exist, unfolding steadily in the background of reality, while life continues on much smaller scales, at much faster tempos, with concerns and joys that matter precisely because they are immediate. The universe is large enough to contain both. As awareness settles back into the present, the idea of immensity does not need to stay sharp. It can soften. It can blur at the edges. It can become less about numbers and more about a general sense that there is more going on than what fits inside any single moment. That sense does not need to be held actively. It can be carried passively, like a distant landscape remembered rather than constantly observed. There is no requirement to draw conclusions from this, no lesson that must be extracted. The value lies in exposure, not resolution. In having allowed the mind to stretch outward, then return, without forcing either movement. The giant galaxy continues to exist whether or not it is thought about. Your life continues whether or not you consider cosmic scale. The two are not in competition. They are simply different expressions of the same universe, operating comfortably at different levels. As attention returns fully to where you are, the immensity does not disappear. It recedes gently, becoming background rather than foreground. It does not need to be remembered actively to remain true, and in that way nothing really ends here. The universe remains open. Understanding remains incomplete. Discovery remains ongoing. What changes is only where attention rests, for now carrying with it a quiet awareness that somewhere, far beyond familiar stars, a galaxy of impossible size continues its slow, patient existence, unconcerned with whether it is being imagined, and content to remain exactly as vast as it is.